Hello, this is Jason Kendall, and welcome to the next of my Introductory Cosmology lectures. I'm continuing the series based on Dr. Barbara Ryden's textbook, Introduction to Cosmology, and we're up to Chapter 3. If you're just tuning in for the first time, please go back to my Cosmology playlist and watch the series in order, starting from Chapter 1. Chapter 3 deals with some elementary concepts in spacetime, and I'm going to contrast the Newtonian idea of space and time to the elementary ideas of Einsteinian relativity. But before we begin, I just want to give a big shout out to my Patreon supporters and my YouTube members. Their support means a lot and helps me to deliver more of this content to you. Both my Patreon and YouTube supporters always get first views of all my videos, as well as some other nifty little perks. So thanks to you for all who are supporting. Now, on to cosmology. There's a long history to the idea of the force and how we get to the idea of the gravitational force. Aristotle, in the lower left, from the 4th century BC, said that earthly objects followed straight lines, quote, to the center. This means that they're attracted to the Earth's center because of their natural motion. Yeah, the ancient Greeks did know that the Earth was a sphere. Aristotle also said that celestial objects follow curved lines that never end. This means that they're not attracted to the Earth's center, but rather stay fixed on the celestial spheres. There was no reason for this other than philosophical codification and a classification of the well-known phenomenon of the motion of the stars and planets. He did not posit any reason other than the celestial motions are perfect and that earthly motions are corrupt or impure, and thus they must be different. Impurities came from death and decay and sank into the ground. Celestial things were known to repeat for all known history and never sink into the earth. That's not science and doesn't give the reason for there being these two realms. Claudius Ptolemy, mapped the celestial motions and created a model by which people could predict the movements of the planets and stars. He was a 2nd century mathematician and philosopher, and his Earth-centered universe held sway until 1610. It was these measurements that were passed down through the centuries that made their impact. Nicholas Copernicus, who lived between 1473 and 1543, created a sun-centered model that ushered in a whole new line of thinking that, amazingly, arose from his studies of Greek antiquity, where Aristarchus had proposed a heliocentric model well after Aristotle's philosophy had been written out. It was the lack of naked-eye stellar parallax rather than some religious viewpoint that led geocentrism to be preferred by Plato, Aristotle, and Ptolemy. That this was picked up by the nascent Christians and incorporated into biblical scripture is where it became dangerous to assert heliocentric models. The influence was big on Copernicus. He, like Ptolemy, posited that the heavens were perfect, so all motions were in perfect circles, and his model included more of the same circle in circles than even Ptolemy's geocentric model did. But it was this idea of his, this heliocentric idea, which caused a lot of waves. He'd created the idea sometime in 1514, but didn't allow this book to be published until after his death in 1543. He, too, did not explain the celestial motions, but rather made a new model based on ancient Greek and Islamic writers, rather than really any new observations. Thus, it was more of a deep philosophical perspective change from the prevailing view that had taken hold from Aristotle's philosophy of long ago. Galileo Galilei picked up on Copernicus's ideas in 1610 with his first book, The Starry Messenger, which detailed his observations through his far-seeing look-glass or telescope. Galileo strongly advocated Copernicus's ideas, much to his detriment, but he advocated them based on his scientific observations of Venus, the Moon, the Sun, Jupiter's moons, and the stars of the Milky Way. His book, A Dialogue Concerning the Two World Orders, inflamed church leaders, especially the Pope, who was actually a friend of his. While Galileo was under house arrest, he did pen more physics books. Simultaneously to Galileo's travails, in 1609, Johannes Kepler published his Astronomia Nova, in which he elucidated his first two laws of planetary motion, that things move in ellipses and the equal areas equal times law. He also posited that some force, kind of like magnetism, must be acting on the planets from the sun to keep them in these motions. He later discovered and published his third law, the p²= a³ law. All of his work was based off of observations taken by Tycho Brahe. It was the combination of these new observations, the accuracy of the predictions, and the revival of ancient Greek heliocentrism by Copernicus and Galileo's audacious public outreach efforts that finally broke geocentrism's grip. This allowed for the rational study of the heavens and opened up all scientific progress on all fronts. In 1687, Sir Isaac Newton first published his Philosophiae Naturalis Principia Mathematica, or the Principia for short. In it, he detailed his laws of motion and formally defined the concept of a force. As a preliminary, all of his laws of motion apply to all matter. So then, what's matter? To answer that deep question, we start with the first law, the law of inertia. Let's say you have some object. Doesn't matter what it is. If it's at rest, it'll stay at rest. If it's moving in a straight line at a constant speed, it won't change direction or speed. Both of these statements will always be true unless the object is acted upon by some external force. Then it will start moving in some direction, or will change speed, or direction, or both. This idea of inertia is the obvious tendency of objects to resist changes to their motions. This idea originally came from Galileo, who used it as an argument in favor of Copernicus. Galileo thought about it in his windowless boat on a still glassy sea analogy. But Newton codified it into a coherent statement as a fundamental law of nature. Newton's second law is that a net external force applied to an object causes the object to accelerate at a rate that is proportional to the force and inversely proportional to its mass. This is the famous F equals ma law. If the net force is zero, then there is no acceleration, just as the first law states. So really, the first law is a special case of the second law. Inertia is defined in the first law is really more of a philosophical statement that tells us about mass. Mass is that thing or whatever that it is that gives matter inertia. Massless things, therefore, as per Newton, wouldn't experience inertia. However, if it's matter, it's got mass, and which can be understood by its inertia. And this is a really important idea. So back to the second law. This law then defines the notion of a force. A force is anything that causes a mass to accelerate, and mass is an intrinsic property of an object. It is the same independent of where it's located in the universe. Just to be clear, mass is not the same as volume or weight. Volume is the size of an object and its extent in space, but a kilogram of feathers takes up a lot more space than a kilogram of lead. And weight is actually the measure of the force experienced due to gravity or some accelerated motion. The force of you standing on a scale can be mimicked if you squeeze the scale between your hands, and this assumes that you're pretty strong. So the pound is not the same as the kilogram. Pounds are forces, kilograms are masses. Just to be clear, the international standard of mass is the kilogram, and a kilogram weighs about 2.2 pounds on Earth at sea level, but only about 0.3 pounds on the moon. But in both places, that bag of feathers or that block of lead is still just 1 kilogram. Now, Newton's third law is the one that really trips up a lot of people. For every force, there's always an equal and opposite force. For example, when you hit a ball with a bat, the bat hits the ball with exactly the same force as the ball hits the bat. So why doesn't the bat fly backwards into the bleachers as far as the ball goes away into the field? First, the bat is more massive, so its inertia demands that it resists motion more. Second, it's also attached to a person who helps add inertia to the hit object. Third, that person is bracing against the ground, which absorbs the hit too. The ball, on the other hand, is just itself, with nothing but air to help push back. So off it goes. Just to be really descriptive, Newton's third law states that when object X exerts a force on object Y asserts an equal and opposite force back on object X. Kind of confusing, but that's why I did the ball analogy. Looking at our diagram, we just see that F1 equals minus F2. So forces also have direction, opposite directions. Finally, we can implicitly define the concept of momentum from the first and second law. Momentum is the product of something's mass times its speed. A force applied through some delta t will cause a change in the momentum by, in the simplest case, changing the velocity, delta v. By the way, velocity is speed going in some direction, so there's always 2 bits to it, and all these add up to give us a really good picture of forces. They act on matter. Matter resists the change via inertia. Forces act through a time interval and must have some cause. And all objects can have their masses determined by applying some force to them and seeing how they accelerate. Thus, Newton defines for us the idea of inertial mass. This adjective applied to mass should scare you. It means that there might be some other kind of mass. But this all gives us Newton's ideas in a nutshell, and the giants whose shoulders he stood upon to get there. Let's continue thinking about things in a Newtonian way and compare the four known forces. First, let's look at the strong and weak nuclear forces. These bind protons to neutrons inside nuclei and mediate the nuclear reactions and radioactivity. Their ranges are extremely short and they are extremely powerful. By short range, we mean the idea of an atom size is about 10 to the minus 10th meters, and the size of a proton is about 10 to the minus 15th meters. As you can see, the weak force acts on a size scale that's 1,000 times smaller than a proton, and the strong force acts on sizes that are right about the same size as protons. Next, the electromagnetic force binds electrons into nuclei to form atoms. It also binds atoms to other atoms to form molecules, and they therefore mediates and determines chemical reactions. It, like the previous two, is extremely powerful compared to the gravitational force. The electromagnetic repulsion of two protons close to each other is 10 to the 36th times stronger than their gravitational attraction. The electromagnetic force is an inverse square law, where the force of attraction or repulsion drops off as the distance squared between the two charges. Now, we know that the protons in a nucleus of an atom are pushing against each other electromagnetically, but yet they're captured by the strong nuclear force. The attractive strong nuclear force, therefore, must be stronger than the electrostatic force to hold the protons together in the nucleus. The separation at which the electric repulsion becomes stronger than the nuclear attraction is about 4 proton diameters. At this distance, which we'll call the range of the nuclear force, and that's about 10 to the minus 15th meters, it can be determined by looking at the stability of atomic nuclei. Oddly, the strong nuclear force doesn't actually decrease with distance. What happens is that as you stretch the bond between two quarks, for instance, more and more energy needs to be invested until there's enough energy to create a new quark-antiquark pair, at which point the bond breaks and transforms the particles of the stretched out quark binding and make them into a new particle. When we therefore speak of the strong nuclear force, as applied between nucleons, i.e. protons and neutrons, we're really mostly talking about the exchange of two quark mesons in the form of pions. In contrast, the weak nuclear force is what's called a Yukawa type force. This kind of force is characterized by a potential of the form of inverse r times the exponential of, say, minus kr, where k is some constant. So therefore, at a short range, where this kr, which is the part of the exponent of the e, is very small, the exponential term is just 1, and the potential becomes an inverse r potential, which then translates to an inverse square force law. Therefore, at very short subatomic ranges, the weak nuclear force is actually very similar to the electromagnetic force, and that's what got some people the Nobel Prize a while ago. But as soon as this exponential term becomes big, the force rapidly vanishes and becomes undetectable. In short, neither nuclear force behaves like a true inverse square law, but the gravitational force as conceptualized by Newton is an inverse square law. As envisioned by Newton, this force binds massive objects together on large scales and mediates orbital motions and tells cats which way is down so they can land on their feet. And since it's a force acting on masses, this means all of Newton's laws of motion apply. In contrast, Einstein's conceptualization of gravity is that there is no force. Moving masses simply follow the shape of spacetime. In practice, these two ideas about gravity only differ when there are very high speeds, where the maximal speed is encountered, the speed of light, and at extremely deep gravitational minima. But this latter phrase is how we talk about space and time in Newtonian language. But when we think of an Einsteinian, we say that it's a strong spacetime curvature. When speeds are slow and minima are shallow and spacetime is lightly curved, the mental frameworks of Newton and Einstein are indistinguishable. At this point, we need to do some important background on how classical and Newtonian space and time are conceived. The name for the shape of space and time in the Newtonian world is Euclidean. This, of course, comes from Euclid's 3rd century BC book, The Elements, in which he describes the postulates for all geometry. Euclid first wrote down and defined the concept of a straight line. The idea that only one straight line can be drawn through 2 points comes from him. That straight lines form triangles with straight sides arises from him. These notions are very familiar to everyone and underpin the thing we call common sense. Euclid's geometry was also highly idealized. This follows from the Greek concept of perfection and divine nature of numbers. As such, he wasn't really interested in measurements of straight lines on curved surfaces or lumpy surfaces. He was interested in the abstractly pure linear geometry with all the two-dimensional flat surfaces. He was also interested in how perfect triangles, squares, and pentagons made the Platonic solids, which we now see commonly as interesting dice for role-playing games. His notions of geometry were placed in a spatial, or more specifically, a topological construction of space itself. His postulates assumed an infinite space where you could set down straight lines going on to infinity, where they may or may not intersect, depending solely on their orientation. Also, as a mathematician, he imbued his writing with a sense of seeking out the truth of eternity. So, his studies separated the notions of space and time. In fact, his whole exploration was into the infinitudes of number and space. To him, they were the same. To that end, we call flat space Euclidean. By flatness, we'll mean that if you take a triangle of any size or arrangement and place it anywhere in the universe, it would look exactly the same in all ways. There is no positional or orientational variation in space that would alter or change any aspect of the triangle. This qualifies as a commonplace idea. It's the one you probably feel intuitively about space and that Newton would have been steeped in and knew very well. Let's now look at what might be a pedantic but very important quality of space. Nowadays, we think of spaces not just as filled with points, but also add an understanding of the distances between those points and the orientation of those positions in space. We choose an arbitrary origin in space in which we can measure any distance in any direction. This origin has nothing to do with the center of space. It's just that where we define our starting point for all measurements. As Dorothy said, there's no place like home. Next, we experience only 3 spatial dimensions, casually known as up, down, back, forth, and left, right. So if we wish to know the location of a point in space, we use vector notation. The 2 vectors u and v have 3 coordinates which show how many straight line steps we take in each given dimension to get to that point. The blue spatial grid helps show that. We call x left, right, y is back, forth, and z is up, down. The length of a distance from the origin in x, y, and z could have magnitudes of u1, u2, and u3, or v1, v2, and v3. In this diagram, we only show one vector from the origin, but we can have infinitely many such vectors. Here, the red arrow is the vector terminating at the destination point. The length of this arrow is the distance from the origin to the point that's the tip of the arrow or vector, and we'll call that length the Euclidean norm. It's pretty easy to see that this is just the extension of the Pythagorean theorem into 3 dimensions. That's what that bar bar u bar bar means. It's an extension of a squared plus b squared equals c squared for right triangles into 3 dimensions. The rectangular box in the grid shows us that this is just the distance from one corner of the box to the opposite corner. If you project the arrow onto any of the sides of the box, or rather look at the box and straight at one side, you will see a right triangle. There will be 3 projected right triangles for the 3 symmetric sides of the box. Once we have the notion of distance from the origin to any point using the definition of the Euclidean norm, we can then use the definition of the inner product to get the distance between any 2 points, or if you will, the arrow tips of any 2 vectors. If you look carefully, you'll see that the distance between vector tips u and v is equal to the norm of u minus v, in parentheses, or together. But wait, if you see that big equation, v1, and set v1, v2, v3 to be 0, then you get the original definition of the norm. Therefore, the distance between 2 points can actually be thought of as moving the origin along the vector v and then determining the distance from that new origin to the point at the tip of vector u. All this is possible because we move in straight lines, and as we move in straight lines, we measure each part of the space in which we endlessly travel exactly the same way. There are no kinks, holes, or loops in Euclidean space. There's nothing to dodge or avoid or go around. Also, if you let this set of vectors sit for 1 billion years and come back, nothing would change. Euclidean space stays the same. Well, wait then, what about time? That's pretty easy here. Time is the same for all observers everywhere in Euclidean space. All clocks tick at the same rate, and all clocks everywhere are completely in sync with each other. Time is the same for everyone, no matter where they are or how they are moving, and time is not linked in any way to Euclidean space. They are completely separate philosophical entities, and the Greeks and Newton had no reason to think they were related in any way. In that way, we can visualize all space as kind of moving uniformly and regularly through time. And that's what the other diagram is showing. Pretend the universe is instead a two-dimensional flat sheet, and every second the grand universal clock ticks, and at each tick a snapshot is taken. This distance in time will be the same between each snapshot sheet across the entire infinite plane of the universe for every location in the universe. If nothing spatially moved in the universe, then the only travel would be forward in time 1 second tick at a time. This big sheet analogy is not going through another spatial dimension, it's moving through time. Thus, this grand cosmic clockwork is how Newton did conceive of time. This was his philosophical basis for the laws of motion, the calculus, and his mathematical conceptualization of gravity. As for Euclid, he sought the unchanging perfection of pure spatial geometry and mathematics, the constancy of the flow of time, and its complete dissociation from space was so inherent to him that he didn't even bother mentioning about it in his writings. Here we see the amazing definition of the force of gravitation. In Newton's idea, whatever the forces are that cause accelerations can be due to many things. You can throw something can explode and push things around, something can be pushed by flowing water, and something can be pushed or pulled by horses. Warm winds may even lift hot air balloons, and so on and so on. But gravity was new and different. Gravity, as Newton conceived it, is a force that is a universal property between any two masses and their relative distances. The force is defined and understood to be proportional to the product of the two objects' masses and inversely proportional to the square of the distance between them. What's even more interesting is that Newton did not posit that there would be any change in this force due to the object's composition or when the objects happened to exist. Mass and distance were the only things that went into the consideration. Now, for the initial understanding of gravity, we need to use the idea of a point mass. This means that the mass lives or can be considered to live, all concentrated at one point in space. Then the distance between any two point masses is easily understood using the Euclidean norm we just looked at. But if there are two planets, say, that are really big and are pretty close to each other relative to their sizes, such as the Earth and Moon, then we have to add up all the contributions from every little rock from the surface all the way down to the core for both the Earth and the Moon. The sum of all these little bits on each other's little bits and their requisite distances works out quite nicely to be represented by their centers of mass. We can regard all of a planet's mass to be at a point called the center of mass. It is that center from which we measure the distance, just like you see on the diagram to the right. We do know that planets orbit each other and that somehow the tides are related to this. I get into the tides and differential gravitational fields and rotating reference frames in a different video in my series, which I invite you to go take a stare at when you're done here. In the meantime, what matters is the primary interaction between their centers of mass for the classic equation you see here. And it is this equation that can be used to chart all the movements of all the planets about the Sun. It can chart the movements of comets and tell us nearly everything about the movements of stars around the Milky Way. And it's this equation that even led to the discovery of dark matter. It was also of some use in Newton's study of falling apples. By the way, the negative sign equation is meant to indicate that the force is attractive between the two masses. They fall towards each other, so the acceleration is such that the distance between them decreases. Now we look at one of the most important and frequently overlooked aspects about Newtonian gravity. There is no explicit time dependence for his force. It just is, and its effect is just present. Gravity's influence travels very fast, likely instantaneously. This means that if there are two planets separated by a big distance and one of them breaks apart into two big pieces and one piece moves away due to some force, this change is propagated to the other planet instantly. Or if two very massive planets are separated by a very big distance, so big they cannot see each other, and if the distance changes rapidly, then the force immediately changes, with the knowledge of that change happening at the exact same time. And there isn't any seen or perceived mechanism. This was a big unsolved problem since its origin in 1687. A fellow of the Royal Society, Richard Bentley, seen on the right, was interested in natural theology and developments in new physical sciences, and it was these subjects upon which he frequently corresponded with Newton. Importantly, in 1713, Bentley was in charge of the second edition of Newton's Philosophia Naturalis Principia Mathematica, or, as it's known in shorthand, the Principia. He often wrote to Newton about the cosmological implications of Newton's gravity, stating that the stars should all collapse into themselves under Newton's gravity, and Newton, of course, had no good answer. In fact, Newton was deeply uncomfortable with the notion of action at a distance. In 1692, in a letter to Richard Bentley, he wrote, "That one body may act upon another at a distance through a vacuum without the mediation of anything else, by and through which their action and force may be conveyed from one another, is to me so great an absurdity that I believe no man who has in philosophic matters a competent faculty of thinking could ever fall into it." Wow. For his laws of motion, he used this phenomenon of motion to explain the origin of various forces acting on other bodies. But in the case of gravity, he was unable to experimentally identify the motion or object or thing that produces the force of gravity. In 1713, in the second edition of the Principia, Newton wrote, "I have not been able to discover the cause of these properties of gravity from phenomena, and I feign no hypotheses. It is enough that gravity does really exist and acts according to the laws that I have explained, and that abundantly serves to account for all the motions of celestial bodies." Wow. Newton punted on the idea of how gravity worked, because he couldn't discern any understandable mechanism. He was also greatly struck that the motions of the planets as well as the terrestrial objects could be explained and modeled by his laws of motion and his laws of gravity. This is a great philosophical conundrum, and it stayed with science for an extraordinarily long time. There are, in fact, only a few things in science that we call laws. We call ideas that are matched by a preponderance of evidence theories. These theories are very good explanations of currently known data and often apply to just limited regions of measurements or conditions. However, laws, such as Newton's laws of motion and his law of gravity, are so well studied, understood, accepted, and are used in such a broad category of phenomena that we have extraordinary confidence that they will never be superseded by any observation. That's what makes them laws. Theories, by comparison, are subject to being thrown out if new observations or experiments invalidate them. Strictly speaking, so are laws too, but the chance that they will be thrown out is practically, and for all intents and purposes, zero. Here, Newton expressed great confidence in his law of gravity, which has held up for nearly all known phenomena for more than 300 years, all with no explanation or even a guess at the underlying mechanism. In order to discern the motions of terrestrial and celestial bodies, Newton had one great underlying assumption baked into his laws of motion and into his law of gravity. It was that the mass of an object as measured by its inertial properties is exactly the same as the mass that creates the force of gravity. Here I've shown that by equating F equals ma with gmm over r squared, and labeling the mass under influence, here a brick with wheels, as both an m sub g for its gravitational mass and m sub I for its inertial mass. Strictly speaking, these two measures of mass describe two completely different phenomena, and there is no absolute need a priori for the measures of these masses to be the same in each instance, and to be ascribed to the same property. Gravitational mass could have been very similar to the electrostatic charge. Its force is given by F equals Q1 Q2 over the distance squared, where the force experienced by two charges is proportional to the product of their charges divided by their distance. If the electric charge is present on or embedded in some kind of object that has mass, then the force will cause that mass to accelerate. But the charges have no relationship at all to the masses of the objects they live on. They're both different properties of the same object with no interdependence between them. Now, if the gravitational mass were some kind of charge that is a property of stuff that is different than the mass that resists motion via inertia, then you should be able to measure their difference. Here in this diagram, m sub circle with a plus is m sub Earth, is the mass of the Earth, or the green ball, the wheeled brick, an excellent toy that is available to you from, say, Amazon.com, would have a gravitational mass of m sub g. The force due to gravity is just the product of their masses divided by the distance between their centers of mass, d squared. Now, if we use our hand to push on this wheeled brick, then it will resist the acceleration with an inertial mass of m sub I. Newton's great leap, or assumption, was that these two processes yielded exactly the same measurement for mass. And because Newton equated the inertial mass and the gravitational mass, we call this incredibly important assumption the equivalence principle. And we can test this in many ways, but an important test would be if two completely different materials with differing masses fell at different rates in the location without any air resistance. David Scott, Apollo 15 astronaut, made such a demonstration on the moon on August 2nd of 1971. Let's watch.
Jim, we copied both solar wind and penetrometer drum in the ETB.
Not quite yet. I haven't put the solar wind in yet, but I will shortly. I want to watch this. Joe, you have a good picture there. I've got
Beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the two of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
Superb.
So how well known and tested is the equivalence principle? To understand that, we want to measure the acceleration of masses in a known gravitational field that are very near to each other and see if they differ at all. The equivalence principle posits that the ratio of the gravitational mass to the inertial mass is exactly 1, but any differential acceleration in some experiment will indicate that the ratio is not exactly 1. Let's look at some recent tests of the equivalence principle. Both of the two example tests are from the University of Washington, were the torsion experiments that you see listed here. A classic type of torsion experiment was first devised by Laurent Utvush in the 1880s and early 1900s. This experiment was essentially two differing masses on either end of a beam, kind of like an imbalanced barbell. This barbell was suspended in the middle, well, not really in the middle, but off-center, by a very sheer but strong wire of known tensile properties. This is all set up to balance three forces: gravity pulling on each mass, the tension of the wire, and the centrifugal acceleration due to the Earth's rotation. Now, if the setup is truly balanced out, then the masses won't be going up and down, and in fact they'll be restricted from going up and down, and the twisting of the wire will exactly balance the centrifugal acceleration due to the rotation of the Earth at the latitude of the experiment, and therefore everything will be at rest. If, for any reason, the bar, after it's all set up to be at rest, starts to rotate, then that would be due to an imbalance in the acceleration field between the two masses appearing in the centrifugal component of the laboratory frame. This rotation would then indicate a violation of the equivalence principle. As you can see from the definition of the gravitational acceleration at the Earth's surface, it is completely independent of the mass of the object, and at sea level for an idealized spherical Earth, it is 9.80665 meters per second squared. So if you have two nearby masses in a near-identical gravitational field, then the difference in their accelerations must appear in the ratio of m sub g to m sub I. Eötvös, in his 1908 experiment, was able to measure this to 1 part in a billion using this idea, and that's really quite excellent. Modern torsion experiments like the ones listed in this, the two that are referenced here, to amplify these ideas, taking into account more and more accelerations in the Earth's gravitational field, and even taking into account variations due to the physical setup of the lab and surrounding environment. The best of these get to 1 part in 10 to the 13th or 10 to the 14th. Then came a space-based test with the microscope mission by CNES, the French Space Agency. Always with acronyms, right? Microsatellite with compensated drag for observing the principle of equivalence. Or, more properly, in French from my AI friend over at Narakit,
Le microsatellite à traînée compensée pour l'observation du principe d'équivalence.
Thanks, AI robot. My French accent would never be as good. This CNES mission was led by a team at the Sorbonne University in Paris, France, with a large team of colleagues and co-authors, and the results were announced in 2017. The microscope mission tested the equivalence principle to an accuracy of 10 to the 15th, 1 part in 10 to the 15th, using the universality of freefall. The satellite payload is composed of 2 pairs of quasi-cylindrical concentric test masses, each made of different materials that all acted as gravitational sensors. The masses were allowed to fall freely while surrounded by their protecting Earth-orbiting satellite, and the satellite had these little bitty electrical thrusters that adjusted the free-falling payload with respect to the satellite, and it's the measurement of these electrostatic forces applied to the masses that allowed visibility into finding a potential differential output for each mass, and they were able to confirm the quality of freefall for these masses to 1 part in 10 to the 15th. This is like knowing the distance between 2 places 100 miles apart to an accuracy of half the size of a molecule of water. For the particle physicists out there, this is really interesting. If there really exists some grand unified theory of everything, meaning quantum gravity, then there would have to be some violation of this equivalence principle. For most predictions of quantum gravity, they state that some equivalence principle violation should appear at the 10 to the minus 13th to 10 to the minus 18th level. For now, though, no such violation has been measured, and the space of allowed quantum gravity theories has greatly shrunk by this measurement in the middle of the range. Basically, at this time, mathematical theories of quantum gravity are way ahead of the experimental capabilities. And the upshot of this is that we shall treat for this video series, as does the entire physics community, that the inertial mass is the same as the gravitational mass, and that gravity, in its currently experimentally confirmed form, is not a charge, but some fundamental property of the thing we call mass. This all goes by way of saying that the equivalence principle is on very solid experimental ground and has yet to be toppled. Now we want to look at how a distribution of mass density throughout the universe creates a cosmic gravitational field. This concept will result in what we call the Poisson equation. Given a density distribution throughout the universe, can we add up all the contributions from all the point masses and create a gravitational field that will tell any kind of test mass how it should accelerate? And the answer is, of course, yes. First, we look at the gravitational acceleration in its vector form surrounding a point mass m. Here, r stands for the radial component of the acceleration, and there's no rotational component to gravity's acceleration. Point masses only pull radially towards the center, and that's what that r hat stands for. It stands for the direction of the radial vector. Anything placed a distance r from mass m will accelerate towards the mass, and that's where the minus sign comes from. And since we said radially, this radial location can be anywhere around the mass. Therefore, we can imagine a transparent sphere around the mass. This sphere encloses the mass entirely, and if we're really smart, we can make up a surface area integral that tests the gravitational acceleration on each little tiny patch of this sphere. That's what we got on the right-hand side integral. That's what that means. So g dot a means the inner product of the vector for the acceleration at a place on the sphere and the vector associated with up from that patch area on the sphere. Well, if we add up all these dot products in the sphere, then we get 4 pi times g times the enclosed mass m. The 4 pi arises naturally because I chose to enclose the mass in a sphere. We can imagine that all the dot products on the left add up to the surface area of the sphere, which is 4 pi r squared. So the two equations you see here are strongly related and tell the same story. The right-hand surface integral is quite familiar to students of electrostatics as Gauss's law. This is, in fact, exactly Gauss's law, but for mass. What we need to do now is extend Gauss's law for gravity into a continuous distribution of mass throughout all space. We need to turn that m, which is for one mass in one place in space, to the mass density as a function of location in all space. Our first step is to expand the idea of the point mass to a distribution of mass across space. So we first define the Greek letter rho as a function of distance from some origin. Remember that this origin is arbitrary. It just helps us with the starting point in space and doesn't mean that there's any center to space. Now this density, rho, describes the density for each point in the universe. We're immediately jumping from point masses to discrete tiny bundles in the vein of Newton's calculus in 3 dimensions. Now, to get a mass out of density, we need to multiply it by some volume. And that's what the d cubed r means. It's a little volume element that looks like a tiny chunk of a sphere centered on the origin. Multiply this volume by the density, and you get a tiny bit of mass throughout the universe. All right, so what's this r-artic mess? We want to find the acceleration due to gravity at the point ending from vector r, as we see on the left. The r minus r tick is the difference in two vectors from the origin. This is basically saying we need to ask what the acceleration due to the tiny bundle of mass at location r tick is at the point we care about, r. The top in parentheses is a vector from r tick to r, and the denominator is the Euclidean norm, or distance, of that vector cubed. The ratio of these two is the distance squared from the bundle of mass to our needed test point. The long S is the familiar integral sum, asking us to add up all these contributions in the entire universe. One goal of all of this is to remove all the yucky vectors from our lives. Vectors drag around a lot of additional work that we might not really need. Luckily, there are things we can do that can hide the fact that we're doing vector calculus. First, let's do a vector dot product on both sides of the equation with the del operator, and this is what we call the divergence. The divergence is roughly a measure of a vector field's increase or decrease in the direction it points, but really it's a measure of the field's tendency to converge or diverge from a point. And that's kind of the point of the acceleration. It's radial, so we're going to expect it to be converging towards that point. To do the divergence, we just take the spatial derivative of the vector with respect to each of the spatial components of the vector. Here, because we luckily use spherical coordinates, we don't have any rotational components to the vector field. It's only a radial function. So we only basically need to take the derivative with respect to r and not r tick. Why? Because we want to use the divergence around our test point to measure how fast the acceleration field is changing as you step towards or away from our test mass's location. And since only the ratio on the right-hand side of the equation depends on r, this leads to the right-hand side derivative with respect to r of that nasty-looking thing in the big parentheses. Now we introduce an important mathematical hackety-hack, the Dirac delta function. It's a known and pretty scary theorem of vector calculus that the divergence of 1 over r squared is 0 everywhere except where r equals 0, and that's where it's infinite. So this is kind of weird, and to take care of it and its obvious non-physical nature, we have the funny Dirac delta function. And this function has two important features. First, the function is zero everywhere, except where its input is zero, and then it's infinite. Second, the integral over all space of the Dirac delta function is 1. This odd definition is both useful and works as a mathematical representation of point-like behavior. We use it for point masses, point electrical charges, and it has lots of other uses in physics and mathematics, but I diverge. So the divergence of that 1 over r squared is definitely 0 at every point except at the spot r minus r tick, where it blows up, i.e. it goes to infinity. But if we take the area integral of a sphere centered on that vector 1 over r squared, we would get 4 pi for any test spherical surface surrounding and centered on that center point. The divergence theorem from vector calculus that the volume integral of the divergence of 1 over r squared must be the same as the area integral of that same sphere of the 1 over r squared vector. A nicer way to think about it is to think that the gravitational field is like a flow inward towards the mass at the center of the spherical boundary surface skin. The amount of flow field going through the surface has to equal the sink capacity of the entire volume inside that surface. So that's really the essence of this divergence theorem. The result of this is that 4 pi times the three-dimensional Dirac delta function is the solution to the divergence of a 1 over r squared vector field, which is exactly what the gravitational field due to a point mass is. A really good place to read a lot more about this is David Griffith's textbook, Introduction to Electrodynamics. It has a couple of really great chapters and gives a full motivation and derivation of the Dirac delta function. So if this was confusing, I'd suggest looking that up. The next thing we're going to do is plug this result back in, and it makes a lot of things really easy. The Dirac delta function is 0 everywhere except where its argument is 0, and its total integral is 1. This means that if we look closely at this, the Dirac delta function will pick out the density at r. So you integrate it over r cubed tick, and it's going to pick out that value at r. Let's see what that looks like. And there it is. It's really simple. We see that the divergence of the gravitational field is proportional to the density of the matter at the point you're measuring. That should make sense. The divergence is a measure of the flow of the vector field towards or away from some point, and we know that's related to the density of material at that point and the mass that's contained near that point. That's exactly what we see here. Now we use the fact that gravitational acceleration is not rotational, so it doesn't have a curl, and that's what that del cross g equals 0 means. If this is true for any vector field, then we can easily define the source of the gravitational field. The gravitational acceleration is therefore definable to be the gradient of some scalar potential. Well, what's a scalar potential? Well, it's like a topological map. At every point in every location, there's a scalar number, height. The gradient points down the slope from higher numbers to lower numbers. Thus, each topological line is an equipotential, where the acceleration of a point depends on how near the next topological line is down the slope. Further, the arrow of down has to be at a right angle to the topological line oriented down the mountain. And all of these topological lines are identical heights. So at each point in space has some value for this potential. Elevation on a map is like this. There's no place where the elevation doesn't exist, and we only define the 0 point to be the sea level of Earth. But sea level itself is defined to be the radius of the Earth if the Earth were a perfectly smooth ball. And it spins, so really sea level does vary by latitude. And once again, go see my videos about rotating reference frames to learn more about that. But back to G. We call the potential phi, and it's negative to demonstrate that acceleration happens towards the mass that sources it and not away from it. Finally, the divergence of a gradient is the Laplacian of the potential. And this is the Poisson equation. This is the modern representation of Newton's law of gravity in a non-vector format. This equation shows that if we can determine the map of the gravitational potential, we can understand the density distribution. Likewise, if we know the density distribution, we can evaluate the potential. Typically, this formulation is shown because you can see that there are no vector quantities. This makes many gravitational problems a lot easier to solve. Both the density and the potential are scalar properties with no associated directionality. They're just values in space. The way to read this equation from left to right is the acceleration of a point mass due to the potential in space is a result of how matter is distributed in space. Or matter density distributions tell all other masses how to move. Or the shape of the gravitational map of the universe is determined by how matter is distributed in it. All right, now let's finish up by looking at the nature of the potential and the gravitational potential energy, which are different things. The gravitational potential can be described in two ways. One, on the left, is for a distributed mass, and on the right, for a point mass. Now, the integral on the left integrates all space to give the potential. And it seems kind of odd since we are stating that the potential is at one point. But the potential at that point does depend upon the matter distribution at all other points in space. And going back to the topological map idea for a moment, we have to reference against all other points on Earth, specifically sea level. Likewise, this integral abstracts all the gravitational fields at all points due to the density and the distance from them. On the right side, we see the far simpler concept of the potential as a function of a single point mass. Again, we want to use the scalar quantity of the potential because then we can ignore all the vector quantities for things like force and acceleration. And we can always get the force field by taking the gradient of the potential, and then we can get the force by multiplying the force field by the mass of the thing in that field. This potential is different than the potential energy. That's because energy is force times distance. So that's how that U of G shows that. One way to think about the potential is that it's the gravitational potential energy per unit mass. This is easily seen for a point mass m at the origin, which takes the form of U of G is equal to some mass times phi of r, where the little m harkens back to our brick on wheels. But that's just a long-winded way of saying that the gravitational potential, or just potential, is not the same as the gravitational potential energy, though they're simply related. Let's get back to the Poisson equation. It can be thought of as relating the gravitational slope of flat space that pulls on and is created by the matter density throughout space. Notice that this entire idea of the Poisson equation is built on the foundations of infinite space, a universal and separate clock, and a spatial topology that can be described as flat and Euclidean. And also, there's no mechanism for it. In the Einsteinian world of general relativity, all of these ideas can be and are violated and changed, and we get an explanation. This means we'll also need a fully relativistic version of the Poisson equation, and that'll be coming soon. That was a lot, but it sets us up nicely for our transition into the way of Einstein, that will motivate both special and general relativity. I'd like to thank my Patreon supporters and my YouTube subscribers, as well as all the great comments on the videos, and I hope you'll consider joining me as a subscriber or supporter. Thanks again, and we'll see you next time for Chapter 3, Section 2, The Special Way of Einstein. Hello, this is Jason Kendall, and welcome to the next of my Introductory Cosmology lectures. We're continuing in Dr. Barbara Ryden's cosmology book, Introduction to Cosmology, and I'm on Chapter 3, Section 2, Newton versus Einstein, and this is the Special Way of Einstein, and we're going to be describing the elements of special relativity for this. Before I begin, just want to say thank you to my Patreon supporters and my YouTube members. They're very helpful, and it really helps to get their support because that helps me keep things going. So with no further ado, let's see how special Einstein's way really is. The first thing we'll talk about is the concept of Galilean relativity. Back in the early part of the 17th century, specifically in 1610, Galileo Galilei first announced to the world his discoveries about the Moon, Jupiter, Venus, and the stars of the Milky Way. In his book Sidereus Nuncius, i.e. the Starry Messenger, he detailed his telescopic findings that the Moon was imperfect, and that this meant that the Moon had craters, mountains, valleys, and areas which are dimmer and brighter and higher. These imperfections were counter to the prevailing idea that the celestial bodies were unchanging, eternal, and perfect. Next, he found that Jupiter had its own set of 4 stars orbiting about it. He named these the Medicean satellites, in honor of the Medici family, who were his patrons, and as a powerful family deeply connected to the Vatican, he hoped to gain some money and favor with them. Incidentally, it worked. But we call them the Galilean satellites Io, Europa, Ganymede, and Callisto, in honor of his discovery. But these stars around Jupiter showed that perhaps the cosmos was not firmly geocentric, that Earth was not the center of all celestial perfect motions. Next, he saw many more stars than can be seen with the naked eye. This was in direct conflict with biblical scripture, thus casting doubt on ecclesiastical support of Ptolemy's geocentrism. Finally, he observed the phases of Venus, which could only be explained if Venus orbited the Sun and not the Earth, slaughtering geocentrism permanently. He created a huge stir across Europe and, in fact, got himself eventually in a lot amount of trouble for advocating this Copernican heliocentric system during a time of a religious schism across Europe. It culminated in his great book in 1632 called The Dialogue Concerning the Chief Two World Systems. This book was incredibly influential on the production of physics for the rest of the world, and in it he argued for the Copernican model of the solar system in a rhetorical way that landed him in house arrest for the rest of his life. At the time, one of the arguments against the Copernican model was that if the Earth were rotating to the east, then objects that are thrown or dropped will tend to fall behind and to the west. Now, that was the argument, and of course, that does not happen. Now, Galileo himself, he concluded by his own experiments that this wasn't the case. He happened to drop some cannonballs off a certain tower near his residence in Pisa and found that differently weighted balls hit the ground at the same time and straight down from the tower. But the argument said that if a stone was dropped from the mass of a stationary ship, it should land westward of the mast. Galileo showed that this wasn't true and went further. He stated that this was true even if the ship was sailing at a constant speed in any direction. No matter what, the stone always landed at the foot of the mast. Of course, this doesn't apply if the ship is speeding up, slowing down, or turning. But Galileo reasoned that the size of the Earth was so big that the speed at his latitude would be essentially constant in one direction during the fall of the stone. So this is interesting. This further meant that the motion of a smoothly moving ship on a glassy sea at constant speed could not be detected in any way. What he basically described was what we now call an inertial frame. If there's an acceleration, there's a different thing. That's what we mean by the set of equations we see here. We have 2 observers of the same event. One observer is on the boat and one is on the shore. Each observer has their own set of measuring systems. They each measure forward and back as x, left and right as y, and up and down as z. They all measure time t using a clock next to them. And the equations you see here are how we transform one set of measurements in one frame to the other. One frame, the boat, is moving by the shore at a constant speed v in the x direction. Which direction we use is of course unimportant, so we align our coordinates along the direction of motion just to make the math easier. Here, the boat coordinates are the ones with the tick marks, and the shore or land-based coordinates don't have ticks. If you want to know where one thing is from one moment to the next, like the ball at the top of the mast of the ship, to the man of the boat, it is stationary, i.e. it has not fallen yet. So all the ticked coordinates for the ball are fixed. On the shore, the ball at the top of the mast is going by at a speed v, just like all other parts of the boat. If you want to transform one set of coordinates to another, just use this equation. Now, we let the stone drop. On the boat, we see it land at the base of the mast. It fell straight down, according to the observer, on the boat. According to the person on the shore, they too also see it land at the base of the mast. Wow, this doesn't sound too surprising, but let's think about it for a second. The stone also must have moved to the right, even though it was briefly not connected to the boat in any way. That's what Galileo thought and measured. Ovviamente, the stone did not fall behind. Proprio no. In the inertial frame of the boat, the stone fell straight down as expected. In the inertial frame of the shore, the stone fell to the right, not behind. To see why, imagine that the boat and the stone were completely invisible until the stone was released. Then imagine we can only see the stone as it fell. Because it's falling down due to the yet incomplete concept of gravity, and it was moving to the right, the stone would appear to move at an angle down to the right, like following the hypotenuse of a right triangle. I know, acceleration and all that, but let's keep thinking simple for a moment. Down and to the right at an angle. This is explained for the land-based observers by saying that the boat and all parts that have speed to the right keep that speed no matter their actions. That's the coordinate system transformation equations we see. Furthermore, this means that all the laws of physics are the same in every inertial frame of reference, meaning moving at some constant velocity, which can, of course, be zero. That can be very fast or very slow, and it doesn't matter the relative directions of the two frames of reference. They're all equal. Now, Galileo took his thought experiment further and said this relativity also applied to an observer that's below the deck. Because let's now say you're not on the deck like we have in the cartoon, where you can see things moving by and say, oh, I'm obviously moving to Earth this way. But let's say you're below the deck. Let's say you now set loose some butterflies, or have dripping water, or have a fish tank. The flitting butterflies do not slam into the back of the boat, going at constant speed, or standing still. The dripping water also drops straight down. The water in the fish tank doesn't slosh or get pushed towards the back of the boat when the boat is moving at a constant speed. All moving at a constant speed. Now, of course, if it's accelerating, that does change things. But we're talking about constant speeds, i.e. inertial reference frames. A non-inertial reference frame is one, of course, that's undergoing some sort of acceleration. Now, because there's no way to know that if you're in a fast or slow constant motion frame, or if you're standing still, all inertial frames are equal. This is the key idea of Galilean relativity, and that's what we call their relative motion between two reference frames. And most importantly, every single law of physics is the same for all inertial reference frames. To get something like the situation we have on the left indicates some special activity. Why would the boat leave the ball behind? Well, that must mean the boat is accelerating. So the picture on the left would be true if the boat were accelerating faster and faster. And yes, the falling ball in that case would indeed go behind. But that's due to the acceleration of the boat, which makes the frame non-inertial. Here, the trick is that for short enough times, even non-inertial reference frames can be treated as inertial for short enough times. We should be able to always find some momentarily inertial reference frame. And this is the core of Galilean relativity, that all inertial frames are equal and all observe the exact same laws of physics. Next, we move on to Sir Isaac Newton and his laws of motion. Newton's ideas flowed from a different perspective than Galileo's, and he expressed his convictions in his Principia in 1687, 55 years after Galileo's work. In it, he described his three laws of motion. Of course, the first law is the law of inertia, the second law is the definition of a force, and the third law, which is his equal and opposite law demonstrating the balance of forces. I'm not going to go into great detail on these laws. For that, just watch my introductory astronomy video where I talk about that and all its implications. I'll link that below. With that, the law of inertia is actually a special case of the force law in which there is no force acting upon a mass. Thus, F equals ma, where F equals 0. This would mean the acceleration is 0 for a non-zero mass, and acceleration is the change in speed or direction with time. If there isn't any change in uniform motion due to a lack of acceleration, either the mass in question is at rest or moving in a straight line. Galilean relativity, of course, says that the object moving in a straight line is exactly at rest if you're in the correct coordinate system, i.e. one that's moving with a mass. The first law, therefore, is a direct consequence of Galileo's ship on a glassy sea analogy. That boat was a non-rotating, non-accelerating reference frame. Stated differently, for Galileo's principle of relativity to hold to Newtonian mechanics, we have to begin with a coordinate system in which Newtonian mechanics is itself valid. However, Newton started from a completely different philosophical stance than Galileo. Newton based his mechanics on the notion of an absolute time and an absolute space. As he wrote in his great work in the Principia in 1687, absolute true and mathematical time of itself and from its own nature flows equably without relation to anything external. Absolute space, in its own nature, without relation to anything external, remains always similar and immovable. What this means was that Newton assumed that there was an absolute reference frame in both space and time. Galileo's relativity also assumed an absolute time, but didn't have much to say about the absolute nature of space. Galileo wanted to upset some apple carts, but Newton was looking for greater universal truths, so Newton's ideas carry the weight of being obvious or common sense. Likely, you too think that space and time are both absolute constructs in which we live our lives and things trundle along tickety-boo. What's good about Galileo's relativity is that it does fit nicely into Newtonian mechanics. However, Galileo would assert that even if some absolute reference frame of space and time were to exist, there would be no experiment that could determine it. Now, Newton came along and said, well, wait a second, what about the concept of a rotating bucket? So imagine if you took a bucket full of water and got it spinning at some angular velocity. After some time, the bucket and water will reach some equilibrium. This means that the water won't be moving with respect to the bucket at all. Once this is all set up, the surface of the water will be concave. That is, the surface of the water near the sides of the bucket is higher than the surface of the water near the center of the bucket. Now, if you compare this to a bucket full of water that's not spinning, here the water will be not moving with respect to the bucket also, but in this instance, the surface of the water will be flat across the top. So what's the difference between the moving and still bucket? How can we explain this difference? On one hand, perhaps the only thing we can appeal to, the only facts we can appeal to, are the relative motions of the water in the bucket. But this is the same in both cases. The water is not moving with respect to the bucket. Therefore, the only difference between the two situations seems to be the shape of the water's surface. And on the other hand, there's another ready explanation for the shape of the water's surface. When the water is spun in a bucket, that is, when the water in bucket system is moving with respect to absolute space, the surface forms a concave shape, and when the bucket is at rest with respect to absolute space, the surface of the water is flat. And this second argument, which seems to be logical, is the one that Newton upheld and asserted. Trying to understand the differences between these two ways of thinking is important. Newton's first law is a conditional. In an inertial frame, an object under no forces has constant velocity. Any spinning object thought experiment, such as suppose that some bucket or disk or pizza or whatever is spinning with respect to an inertial frame, for someone who believes in this absolute space, the definition is that there's a frame moving with constant velocity with respect to absolute space. Now, much later than Newton, well, we're diving away from the subject a bit, Ernst Mach defined an inertial frame to be a frame that's at rest with respect to the distant fixed stars. This basically gives the same results as Newton's theory, but only when there are lots of stars evenly distributed very far from us. For other kinds of universes, like empty ones with nothing in them at all except a bucket and some water, Mach thought we weren't justified in saying anything at all. So he only accepted spinning object arguments when they were made in universes like ours, in which case he could say that inertial means at rest or close enough with respect to the distant stars. Therefore, absolute space in Mach's idea was not needed. So when you have a lone bucket, disk, or pizza spinning with nothing else around, you can't say what would happen without assuming of an absolute space. If Mach's theory was right, then you still get some really tiny centrifugal forces from the relative motion of the bucket and the water as the system spun up. And this is like away from Earth, away from any kind of gravity, away from any reference frame, out in space with just distant stars. Also, if the bucket was extremely thick, you'd get some detectable differences between Machian mechanics and Newtonian mechanics. But this is a serious digression. The main point here is that Newton's laws of motion are applicable to Galileo's concept of relativity, but Newton added on the prima facie, apparently common sense idea of absolute space and absolute time. Galileo would have likely been amazed by the laws of motion and have been intrigued by Newton's rotating bucket argument, But he might have been annoyed that his stowaway butterflies might possibly be slammed into lower bulkheads of schooners that are apparently not moving. Now we move on to James Clerk Maxwell and his equations of electromagnetism. Electromagnetism at the end of the 19th century concluded that light waves travel at a fixed speed in a yet undiscovered medium called the luminiferous ether. This fixed ether speed was discovered by Maxwell to be the speed of light. Let's see where that came from. First, let's look at Coulomb's inverse square law, or as it's called in undergraduate E&M classes all around the world, simply Coulomb's law. It calculates the amount of force experienced by one charge at rest due to a second charge also at rest. The force drops off as the distance squared between the charges and is directed radially between them. Defined in 1785 by French physicist Charles-Augustin de Coulomb, it's important to note that this law was experimentally observed and measured. In fact, all of the laws that we're about to look at are founded on experiment and observation. Because it allowed the quantification of about how much electric charge was on or in a particle, Coulomb's law was essential to the development of the theory of electromagnetism and can be considered its starting point. For our current discussion, we note that this force has a conversion factor, epsilon zero, the vacuum permittivity. Epsilon sub zero is an experimentally defined quantity that converts a pair of charges and a pair of distances into a force. We see that 1 over 4 pi epsilon naught has the value of 9 times 10 to the 9 meters per farad. Meters per farad has other meanings in SI units, and it's the same as a Newton meter squared per Coulomb squared, as is obvious from the equation itself. But the SI unit for electromagnetism is the ampere, not the Coulomb. And if we translate it to that unit, we see that it's a Newton per amp squared times a speed squared. And that speed will come up as very important later. In 1820, Danish physicist Hans Christian Ørsted discovered that an electric current creates a magnetic field circling around that current. He noticed it as he moved a compass around a wire carrying a current, and the needle turned such that it always was perpendicular to the wire. This sparked a huge amount of research. He showed this to André-Marie Ampère, who went to do many, many experiments that clearly showed the relationship between an electrical current and a magnetic field, culminating in the experimentally derived Ampere force law in 1825, which you see here. This relates the force per unit length of wire to the product of the currents in the wires divided by the distance between them. Because the left-hand side of the equation isn't just force, but force per unit length of wire, then the conversion factor, mu naught, then must have units like force per squared amp. This is the vacuum magnetic permeability, and it quantifies the strength of the magnetic field induced by an electric current. Officially, mu naught is about 1.3 times 10 to the minus 6th henries per meter, which of course is translatable to other SI units as needed. In 1820, Jean-Baptiste Biot and Félix Savart discovered empirically their Biot-Savart law, which describes and characterizes the magnetic field generated by a constant electric current. Again, we have the permeability of free space mu naught. This again is a conversion factor which is experimentally measured. With these equations, Maxwell had what he needed to begin the work of electromagnetism. For those college students out there, the Lorentz force law, which explicitly relates the force on a charge due to an electric field and a time-varying magnetic field, was derived by Hendrik Lorentz in 1895, well after Maxwell's work. This equation is often used today as the fundamental definition of the electric and magnetic fields. The force experienced by a charge Q is dependent on the electric field E acting upon it. If it's moving with velocity v, then it also experiences a force due to a moving through some magnetic field B. Coulomb's law and the Biot-Savart law and the Ampere law all combine together to shove that charge around. However, this force law was only hinted at by James Clerk Maxwell's groundbreaking work, and it had to wait. From 1855, Maxwell studied and wrote about electricity and magnetism at Marischal College in Aberdeen, King's College in London, and at Cambridge. In 1861, he published On Physical Lines of Force, where he reduced all the current knowledge about electricity and magnetism into a set of 20 differential equations in 20 variables. Maxwell showed that his 20 equations predict the existence of waves of oscillating magnetic and electric fields that travel through empty space. Further, the speed of the waves could be predicted from simple electrical experiments using the data currently available at the time. In so doing, Maxwell obtained a velocity of about 310 million meters per second. In 1865, he wrote in another paper his growing confidence that light and electricity and magnetism were one and the same. Quote, "The agreement of the results seems to show that light and magnetism are affections of the same substance and that light is an electromagnetic disturbance propagated through the field according to electromagnetic laws." His famous 20 equations, now fully developed in their modern form of these four partial differential equations, first appeared in his textbook, A Treatise on Electricity and Magnetism, in 1873. Now let's go through each one of these in turn. First, we look at Gauss's law. Carl Friedrich Gauss derived this relationship empirically from experiments in 1835. It can be summarized as the net electric flux through any hypothetical closed surface is equal to the electric charge enclosed within that surface, divided by epsilon naught. Here, del dot E is the divergence of the electric field, epsilon naught is the vacuum permittivity, and rho is the total volume charge density, charge per unit volume. In Maxwell's time, epsilon naught was measured and known by relating electric charges in Coulomb's law, knowing the amount of electric charge between 2 point-like objects and somehow measuring the force between them. Strictly speaking, the value and representation of this constant has changed through time as various unit standards have been adopted and changed, but that's a side note. We'll keep the vacuum permittivity in mind for later. Next, the oddly named Gauss's law for magnetism. It states that the magnetic field B has a divergence equal to 0. This is equivalent to stating that magnetic monopoles don't exist, which is usually how this equation is named. This idea for the non-existence of magnetic monopoles originated in 1269. Yeah, that's right, 1269, by Petrus Peregrinus de Mercure. In the early 1800s, Michael Faraday reintroduced this law, and it subsequently made its way into Maxwell's electromagnetic equations, as you see here. Gauss occasionally gets this one named after him, too, because of the similarity to the previous equation. But there exist electric charges, right? So why not magnetic charges or magnetic monopoles? Well before Maxwell's time, it was well known that when a bar magnet is broken into two pieces, you get two small magnets, each with their own north and south poles, and this is explained by Ampere's current law. The bar magnet on the atomic level is made of many little circular current rings, each of which is essentially a magnetic dipole. Since a small current ring always generates an equivalent magnetic dipole, there's no way of generating a free magnetic charge. That is, there's no way to break off just the north pole of the magnet. Suffice it to say that no magnetic monopoles have ever been found in any experiments, and not for lack of trying. If magnetic monopoles were ever found, this law would of course have to be modified. There are reasons why particle physicists have hypothesized that they must exist, specifically in the supersymmetry breaking at the time of the universe's inflationary epoch. This should have created a huge number of them, but we see 0. I'll talk more about this in later chapters in the series, but if you want to learn more, go look at my cosmology videos in my Introductory Astronomy section to learn more about magnetic monopoles and their impact in the early universe. But I digress. Let's look at the third equation, Faraday's law of induction. It can be read as the electromotive force around a closed path is equal to the negative of the time rate of change of the magnetic flux enclosed by that path. In 1831, Michael Faraday created an experiment that demonstrated electromagnetic induction. He wrapped two wires around opposite ends of an iron ring. He described that when current began to flow in one wire, a sort of wave would travel through the iron ring, causing some electrical effect on the other wire. He measured a transient current, which he called a wave of electricity, on one side's wire when he connected or disconnected the other side's wire to a battery. This process made a change in the magnetic flux and induced a current. he created a concept called lines of force to describe and explain it. At the time, scientists rejected Faraday's theoretical idea of a line of force, mainly because Faraday did not formulate it mathematically, but only geometrically. This most important exception to this disdain was, of course, James Clerk Maxwell, who used Faraday's idea as the basis for all his theories. Maxwell summarized it in his third equation. Incidentally, this was Maxwell's starting point into electrodynamics, where he discussed at length in his 1855 paper on Faraday's lines of force. The fourth and final equation of Maxwell's laws is an extension of Ampere's 1825 experimentally observed law. Ampere's version of this equation determines the magnetic field associated with a given current, or the current associated with a given magnetic field. However, Maxwell's inspiration was to add a second term, the displacement current, that epsilon dE dt. He reasoned that a current, J, was the same as a changing electric field, perhaps due to a burst of charges moving along. This critical insight allowed him to then hypothesize that light was a form of an electromagnetic wave using a time-varying electric field. Now let's follow along in Maxwell's footsteps and derive his stunning assertion that light is an electromagnetic wave that can travel through empty space. First, we're going to take Faraday's law and we're going to apply the curl to it. Next, we note that in free space or vacuum, there won't be a current, so there won't be anything for J. With that idea, we use Ampere's law with only the time-varying electric field component. Plugging this in, we see that in the second line that we've introduced both the vacuum permittivity E sub naught and the permeability of free space mu sub naught into an equation that only has a bunch of vector stuff and the electric field E. Specifically, on the left, there are only spatial partial derivatives, and on the right, we only have partial derivatives with respect to time. Now, the product of these two constants has the units of inverse speed squared because we have to convert times into distances twice. And since mu sub naught and epsilon sub naught are constant, so are their product. And then we can define c to be the speed of the electromagnetic disturbance propagation. This was Maxwell's great discovery, that all electromagnetic interactions travel at this speed, and that this speed was identical to the speed of light. The speed of light was well known from contemporary experiments, so this great assertion marks him as one of the great geniuses of science. So, how does light travel? Well, we have a curl of an electric field, and this can be readily simplified through vector identities. There are two parts to this. One looks like Gauss's law, and the other looks like two partial derivatives, exactly like Poisson's law from the previous chapter, a Laplacian of spatial derivatives. For the first part, in empty space, there are no charges or currents, so that part's zero, and with that, only the Laplacian term remains. And for this, I simplify the Laplacian to one dimension for our pedagogical ease. That equation, in the fourth step, is a standard wave equation that propagates at speed c with a typical wave equation shown at the bottom. When Maxwell found this solution, he was convinced that all electromagnetic phenomena were the same thing, were composed of waves, and all went at the speed of light. Remember that mu naught and epsilon naught had good measurements at the time, and the reciprocal square root of their product was so close to the value of speed of light that was known at the time by the experiments of Fizeau and Foucault that he found it too compelling to be false. Maxwell, of course, was proven correct, and this making this leap to demonstrate the measurable connection between light and electromagnetism is one of the greatest accomplishments of classical physics. Finally, and critically, his great work was founded on another idea, that is, light's propagation required a medium for the waves. Maxwell dubbed this medium the luminiferous ether. It was a commonplace and seemingly necessary idea that every wave phenomenon required a medium through which it could travel. His work codified the idea of a luminiferous ether, which was now the new hot area of physics for the last part of the 19th century. Now that I've spent a good deal of time setting up the three major accomplishments of classical physics, it's now time to show that they're all mutually incompatible. First, we have Galilean relativity, where all inertial reference frames are equal for all forms of mechanics, and transforming between reference frames is a simple addition of velocities. Second, we have all of Newtonian mechanics with an underlying idea of absolute space and absolute time. Third, we have Maxwell's theory of electromagnetism, where it was discovered that all electromagnetic interactions travel at one speed, the speed of light. Each of these achievements was groundbreaking, developed in response to experimental evidence and held up to the extreme scrutiny by the community of scientists. Then it should be astonishing that all three cannot be true at once. Let's first look at Newtonian mechanics with its framework of absolute space and time and Galilean relativity. If both of these are true, then you necessarily get that the speed of light will be measured differently by mutually moving observers, violating Maxwell's laws. You'll be able to construct a setup where the speed of light can be seen to be going 1.5 times the speed of someone else's speed of light for some pair of observers mutually moving past each other at some constant speed. In order for this to happen, we would have to assume Galileo's axiomatic assumption that there were no absolute reference frames, i.e., all motions are relative. Alternately, if we state that Newtonian mechanics and Maxwell's electromagnetism, then there must be some preferred inertial reference frame in which light travels, violating Galilean relativity. This basically means you'll eventually be able to find some Galilean boat where some experiment will tell you that you're moving at a constant speed, and that boat will have butterflies smashing into the back wall at a constant speed. Maxwell held this position and stated there must be some luminiferous ether that is the medium for light which is at rest with respect to all other movements in the universe. Newton would approve of this idea wholeheartedly. Galileo would say, perhaps, but how exactly would you find this absolute space and time reference frame? I've never seen it, and I don't know how you'd ever find it. Finally, if you hold Maxwell's laws to be true and side with Galileo's relativity, then you find that all observers see the same speed of light no matter their relative motion. In addition, all existing laws of physics in a given inertial reference frame would just stay the same. This is what we trust and assume implicitly when we try to replicate any experiment on Earth or in space. However, it's the particularity of Maxwell's discovery that the speed of light is related to all these known physical constants that are measurable from simple experiments of electricity and magnetism in any laboratory. This will violate absolute space and time because an observer will see the signals from a moving partner to be slower relative to their own because of the constancy of the speed of light no matter the movement of the observer. However, it doesn't ruin Newtonian mechanics in a given inertial frame, since all frames observe the same physical laws. It's just that translating between two frames becomes tricky when the two frames are moving relative to each other at close to the speed of light. This is because the straight addition of velocities between frames, like Galileo would assert, might seem to need to be modified. In sum, these three great achievements of classical physics can't all be true at the same time, and the scientific community had to come to a consensus about where the most fruitful research to resolve this conflict should be engaged. The broad consensus, pushed strongly by James Clerk Maxwell, was that the luminous ether must exist. People took it as an obvious truth that space was absolute and unchanging. There was also no reason for anyone to think that time was anything but a universal thing that permeated all of creation. Remember, at the latter part of the 19th century, the universe was only the stars in the sky and the Milky Way. It was also thought to be ageless, with time just being the thing that we measured out of the years of our lives, and everyone everywhere felt the same flow. This meant Galilean relativity was about to be thrown out. Everyone was convinced that there must be some absolute reference frame from which we can measure absolute space and absolute time. On its face, this seems to be pretty logical. Maxwell derived the speed of light from known experiments and knew it propagated as a wave. Further, as a speed, it meant that something must be moving with respect to something else. To paraphrase Shakespeare's chorus in King Henry V, thus with our imagined wing our swift photon flies in motion of no less celerity than that of thought. Much faster than thought, actually, and with respect to its home medium that had yet to be discovered, the luminiferous ether. This quest to discover and measure this ether, which everyone was convinced must exist, generated vigorous research in the 1880s and onward. Let's presume that the ether is completely undetectable except through its interaction with light. It has no impingement on mass in any way. Now, if the ether was still or stationary, then as the Earth went around the sun, all light rays in existence would experience an ether wind. That's what's indicated by my cartoon. The red hash is the ether that, by being stationary, would create a wind in the direction of Earth's orbit around the sun. For example, if light was radiated in the direction of Earth's motion, then the light would experience a headwind and be slower. Furthermore, if at any given point on the Earth's surface, the magnitude and direction of the wind would vary with the time of day and the season. In order to measure this wind, you would need some source of light that would send rays in two different directions, preferably orthogonal. If the distance they travel is long enough, then one of the two directions will encounter the ether wind and be slower than the other. You can orient these directions any way you want and keep taking measurements. It shouldn't take long to pick up the wind. It was understood that since the speed of light was roughly 10,000 times faster than the speed of Earth going around the sun, the measurement would need to be cutting-edge technology. Enter Albert Michelson, seen at the top. Michelson was fascinated by light for his entire career. After a long history of hundreds of years of numerous experiments to firmly establish the speed of light, Michelson contributed to the effort in 1879. He measured to be 299,909 kilometers per second. In 1881, he invented the Michelson interferometer. A sketch of that is shown here. A source of light is sent towards a half-silvered mirror, which breaks it into two rays of light going to two mirrors. These mirrors reflect the light, which was then seen by a detector. Because the light has a wavelength, this procedure will put the two rays out of phase, creating an interference pattern in the detector. If you carefully adjust the length of one of the distances to one of the mirrors until the rays meet coherently at the detector, you're ready. You then simply rotate the apparatus until the rays become out of phase again. When they're out of phase, this would mean that there is some ether wind slowing down one of the rays as it pushes back on it. My moving cartoon shows this effect on the blue ray. Michelson's first attempt in 1881 was not sensitive enough, and so in 1887, he and Edward Morley made the great improvements and created their famed Michelson-Morley experiment, which you see in the picture. It was also an interferometer, bouncing the light on a much longer baseline with many mirrors. To reduce vibrations and increase sensitivity, it was all set up in a huge block of sandstone suspended in a tub of mercury. In the spring and summer of 1887, the two men labored to find the ether wind. To their great dismay and surprise, they found nothing. All of the runs of their experiment never showed any phase shift. They were forced to conclude that they had a null result. Specifically, they could not observe the expected wind and published it in the fall of 1887, and this is considered the most famous null result of all time. This didn't settle it, though, because people could not believe that this null result was true. Morley himself did not believe his own results and went on to do numerous experiments of ever-increasing sensitivity. All null results. This lack of ether wind was studied and confirmed by many other experiments up until the 1930s, when multiple teams of researchers across the world came to the same conclusion with their own interferometers. The work was considered settled, but so troubling that starting in the 1950s, with the invention of lasers and masers, research happened again on interferometry with even greater accuracy. Dozens of teams across the world used the new technology to try to find the ether until the 1970s. They all failed to find the ether wind. And this put the issue to rest until the 21st century. Starting in 2003, a new resurgence in re-examining this settled science arose due to new theories of quantum gravity, which predict violations of special relativity on measurable scales. These new studies, with the most recent in 2015, showed no ether wind to the greatest accuracy yet, with no evidence found of any variation of the speed of light in any direction to 1 part in 10 to the 18th. We are now forced to conclude, even though it's an astonishing and lightly unbelievable result, that the ether does not exist. There is no medium in which light travels. Returning to Shakespeare, all these grand failed efforts to find the medium of light's waves remind us of the last part of Hamlet's famous soliloquy. All these researchers tried to probe the undiscovered country, from whose bourne no traveler returns, which puzzles the will and makes us rather bear those ills we have than fly to others we know not of. The ill that we have is that there is no medium for light's traversal. Over 100 years of searches by dozens of teams have all failed to find it. But now let's go back to see what happened in the wake of Michelson and Morley's 1887 null result. In 1905, Einstein cut through the difficulty when he published his paper on the electrodynamics of moving bodies. Einstein looked carefully at all electromagnetic interactions and noted how some effects were measured depended only on the relative motion of the objects in question. In so doing, he revived and extended Galilean relativity. Take, for example, a permanent magnet and a conducting metal object. Let's take our magnet and move it past the conducting metal object. Here, the motion of the magnet creates an electric field that induces a current in the conductor. Now, if we instead keep the magnet at rest and move the conductor, the moving conductor will then experience a force called an electromotive force, or EMF, that generates a current, but no electric field was created in the vicinity of the stationary magnet. These two effects were always seen as two different phenomena and treated differently with different equations and different names. But Einstein came along and said that the actual observable effect, the generation of a current, does not depend on which object, either the magnet or the conductor, is in motion, but only on their relative motion. To reiterate, in the case of the moving magnet and the stationary conductor, the movement of the magnet creates an electric field around it, which in turn generates a current in the conductor. On the other hand, in the case of the conductor moving and the stationary magnet, although no electric field is generated in this case, the movement of the conductor through the magnetic field produces an electromotive force, which again results in a current. Einstein's key insight was that the relative motion between the conductor and the magnet produces the same physical effect, an electric current, in both cases, even though the mechanisms are described in different ways. This was an extension of Galileo's boat on a glassy sea. Galileo only considered the relativity of events happening on the boat and being unable to distinguish the boat's constant speed motion from tests done down in the windowless hold. Einstein basically added the idea that if two ships passed each other, each with their own experiments on board their boats, and one boat had a magnet and the other had a conductor, the bosun below decks watching the conductor would know that he was moving with respect to the other boat that had the magnet if he measured a current through the conductor. But he wouldn't again be able to tell if it were his boat that were moving with respect to the shore, or if he were at anchor and the other boat was sailing by. This elevated Galilean relativity up to a new height. As Einstein wrote in 1905, quote, "Together with the unsuccessful attempts to discover any motion of the Earth relatively to the light medium, suggest that the phenomena of electrodynamics as well as of mechanics possess no properties corresponding to the idea of absolute rest. They suggest rather that the same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold good." He called this his first postulate of relativity. All physical laws are valid for all inertial frames, no matter their relative motion. His second postulate is the one that triggers so many Doc Brown wannabes into trying to trick out a DeLorean in their garages and their dilapidated ranch houses deep in the woods. Einstein stated that light is always propagated in empty space with a definite velocity c, which is independent of the state of motion of the emitting body. He goes on to completely adopt the null results of the Michelson-Morley experiment and all its antecedents. Quote, "The introduction of a luminiferous ether will prove to be superfluous as the view here to be developed will not require an absolutely stationary space, provided with special properties, nor assign a velocity vector to a point of the empty space in which the electromagnetic processes take place." This is the core of special relativity. He chose to toss out Newton's concepts of absolute space and absolute time. He chose to throw out your common sense. Making this statement is nothing short of revolutionary. Let's look at some implications for these two postulates. For the first postulate, the laws of physics are the same for all uniformly moving observers, no matter what the speed of the observer is going. Here, uniformly always means with a constant velocity, that is, no acceleration, no turning, no speeding up or slowing down. No such thing as absolute rest, which means that there is no such thing as absolute speed, only relative speed. Any uniformly moving observer can also consider themselves at rest. Every observer also only sees their own time and space as normal. Every possible physical experiment is the same, no matter what your speed is. And here's what happens with the second postulate, that the speed of light in a vacuum is the same for all observers, regardless of their motion relative to the source of the light. This has a lot of implications. The first is the speed of light is a universal constant. We cannot send or receive information faster than the speed of light, and the speed of light does not add or subtract to or from the relative motion of the observer. This has been experimentally verified in all cases. I'll give you the most important punchline here of all. Because of these strange implications, these postulates have been challenged and tested harder than any theory in the history of science. But the degree to which we now trust them has resulted in the odd fact that we no longer measure the speed of light, we define it. In 1983, the International Bureau for Weights and Measures, the international organization responsible for preserving and promulgating scientific measuring standards, held their quadrennial general conference. Prior to 1983, the concepts of space and time were separate. The meter was defined for a long time by the distance between two ticks on a platinum iridium bar at the Bureau in Sèvres, France. In 1960, the meter was subsequently redefined to be a large number of wavelengths of light from an atomic transition in Krypton 86. As for time, the second had been defined as the duration of a gargantuan number of vibrations found in an atomic hyperfine ground state transition of cesium-133. The attendees of the 1983 conference then chose to elevate Einstein's postulate to the level of settled science by defining the speed of light to be exactly 299,792,458 meters per second. This definition then removed the need for the standard meter bar, and now it stands as a museum backup piece. Henceforth, the speed of light was then to be recognized and understood as a fundamental universal constant. Interestingly, this basically turned it into a simple conversion factor between space and time, which were now seen to be aspects of the same entity, spacetime. Einstein's postulates have withstood withering experimental challenges because his assertion that there is no medium for light waves' properties, combined with the erasure of absolute space and time, caused legitimate scientific consternation. Let's now look at the underpinning mathematics that Einstein used to describe his special theory of relativity. After Michelson and Morley revealed their failed attempt to find the ether wind, many physicists, including Voldemar Voigt, George Fitzgerald, Joseph Larmor, and Hendrik Lorentz, were all researching what Maxwell's equations meant and how to accommodate the staggering null result. They all hunted for the transformation between two reference frames where Maxwell's equations were invariant, that is, where you didn't have to modify the form of the equations for any relative motions. They found what was called the Lorentz transformation, shown here, but their combined goal was to preserve the ether's existence. Einstein did his own derivation of the Lorentz transformation for his 1905 paper, starting from his two postulates and arriving at the same set of equations you see here, all without relying on an underlying assumption of the ether or even trying to preserve it. Before we follow his derivation, we need to basically understand what the Lorentz transformation is. First, let's go back to the definition of a relatively moving reference frame. Basically, you can think of them as a coordinate grid that's at rest with respect to a given observer. Each observer can think of their reference frame as a massive cubic grid of meter sticks, and at each intersection in the grid, a clock is fixed to the node. All the clocks in one observer's frame are set up to be in sync, and now, moving relative to that frame, another observer's frame has the exact same arrangement, but centered around him. These two frames are moving uniformly, that is, with a constant speed and no changes in direction or acceleration, with respect to each other. We'll have to pretend that the two frames are made of some ghostly material that allows each other's frames to pass through with them. That's what the diagram on the top left actually means. So, one frame, we'll call it the primed frame, is moving along the unprimed frame's x-axis at a constant speed v. relatively, the unprimed frame sees the prime frame moving to the right, and the prime sees unprime moving to the left. Our job is now to ask, given this setup and that we live in unprime, how do our measurements in unprime transform over to primes measurements? First, we look at the two equations in the green box at the top. Let's say our two events are the turning on of a light bulb and the detector receiving the light. In our home, unprimed frame, the distance the light travels is delta L squared. And that distance is, of course, just like the Pythagorean theorem, except for each coordinate, we have two locations in each dimension, one for the starting place of the light and the other for the detector. Naturally, that distance is equal to the square of the speed of light times the difference in time between emission and reception. This will also be true in primeland. Now, Einstein's postulate is that all observers see the same speed of light. So, c is the same for both equations. We don't put any requirements on any other measurements to be the same, however. Indeed, they can't all be the same. The frames are moving with respect to each other. Both of them lead to that intermediate equation with the delta x squared, delta y squared, delta z squared minus c squared, delta t squared equals 0. They're all of the same form. We'll call that thing here equal to 0. That's in between the green and blue box. The spacetime interval. We usually denote that interval as delta s squared, as you see below. In our little example with the light bulbs, we see that the events connected by the speed of light are called null spacetime intervals because they equal 0. Now, if we do a pair of events that are not connected by the speed of light, like the popping of a cork in unprime and the cork subsequent hitting the wall, what does the frame grid of meter sticks and clocks read in the relatively moving prime frame for these two events? Well, in the blue box, we have two different spacetime intervals, each measured in their own frame. In the light bulb example, the spacetime intervals were the same and equal to 0. Since this isn't a murder mystery, I'll say up front that the Lorentz transformation requires that these intervals are always the same for the same events measured in two different frames. This means delta s squared is the same as delta s prime squared for all frames. I'll justify and prove this later, but for now, let's take it as a necessary thing that the spacetime intervals are invariant. Let's take a look. On the bottom left are Galileo's transformations. These transformations don't on the surface appear to be a good transformation given the commingling of space and time, but they seem to work in everyday life, so they can't be 100% wrong. But if you look at events where you're transforming between two frames at a speed that's an appreciable fraction of the speed of light, then you need the middle set of equations. These are the Lorentz transformations. With this, we now get some odd things. For the x-coordinate, which is the direction of motion, x prime does not just depend upon the speed of the relative motion and the event's subsequent position in unprime, but it also now depends on the time measurement in unprime. That's wacky. Even wackier, the time is no longer universally the same. T prime does not equal T unprime. Transforming unprime time to prime time depends not just on their relative motion, but also on the unprime x position. Again, transforming to a time coordinate in prime, in the prime coordinate system, depends both on the unprime time and the position in unprime. Time and space are interlinked. It means they're really one and the same thing-ish. They're both parts of some broader thing called spacetime. And that gamma, that's what's called the Lorentz factor, and it's a needed coefficient to the transformation equations. It's an interesting thing, because starting with v being the relative speed between the two frames and c being the speed of light, if v is really small with respect to the speed of light, then the Lorentz transformations are very well approximated by the Galilean transformations. But we also see that as v approaches c, gamma approaches infinity faster and faster. This has strange implications, as we'll see later. Just to reiterate, we got the Lorentz transformations because we assumed two things: Einstein's second postulate and the invariance of the spacetime interval. Again, what motivates that second one? The spacetime interval is now the thing that is measured in a given inertial reference frame. All the laws of physics and mechanics are the same, which would include the nature of the measurements of distance and time. So the space-time interval invariance is like saying clocks work the same in both frames and meter sticks are the same things and do the same thing in both frames. This Lorentz transformation is central to special relativity. And notice it doesn't ask us to show an absolute space or time. It only shows us how to go between two moving frames, whether very fast or very slow. And the nature of these moving frames' coordinates show that each frame measures their own time and their own distance, and each is at rest in their own frame, and each looks exactly as you would expect them to look. It's just like if you were in some room with clocks and meter sticks doing an assignment for a physics class. The same would be true of the moving frame. But when you're chatting with each other about the events you both measure in different frames, you get different results. Okay, now let's see where this transformation comes from. Let's quickly derive the Lorentz transformation. We'll just use Einstein's postulates and some mathematical definitions that don't have any physics attached to them to do it. First, we're going to use the null space-time interval and try to relate the prime to the unprime system. That's the ct squared minus x squared across the top. Again, we assume that we're watching something at rest in prime frame and it's moving by on the x-axis at speed v. So now let's go to the green box. Inside the green box, we have the definition of the hyperbolic sine, cosine, and tangent. Well, strictly, this is not just the full definition. This is just the identities based off of these mathematical curiosities. High school students the world over pore over these in problem sets given to them by teachers bent on getting kids into engineering programs. The cosh, sinh, tanh in their functional forms are lightly nasty-looking exponentials, which you can Google or look up in a standard textbook with ease. Anyway, it's important for the space on the slide that I just simply define big C and big S. All right, now in the blue box, we construct by just playing around with the substitutions for a while and get this general solution. So where did this come from? Well, we didn't start with big S and big C where they are. We used dummy letters instead and plugged them back into the top unboxed equation. So after much simplification, the dummy letters are identified with big S and big C because of the identities that you see here. As an exercise, just plug them into the top equation and do the algebra using the identities in the green box, and you'll see how it works out. Now we add two facts about the setup. First, we are at rest at the origin in unprime, so x equals 0 always. Next, we see this fact or observe this fact from prime world's perspective to be us falling backwards at a speed v across t prime. That's the measurement of me sitting in one place as seen from prime world's perspective. We take those two facts and plug them back into the blue equations to get the ones in the gray box along the bottom, which is x prime equals ct big S and ct prime equals ct big C. All right, now across back over to the top, the purple box is what we get if we take those last two equations on the bottom and we divide x prime by ct prime. Obviously, that's just v minus c, but sinh over cosh gives tanh. That opens up some doors. We now know that big C is identically our gamma factor, and big S is now that gamma factor times minus v over c. Pushing that back into the equations in the blue box, we get the red box equations. Comparing them to our original definition of the Lorentz transformation, we see that they are the same. In sum, we took the identity of two null spacetime intervals as seen in two relatively moving frames and asked what prime sees as I sit in place in unprime. Now that's all well and good for null spacetimes, but if we're not talking about light, we necessarily have non-zero spacetime intervals. How do we know that the spacetime interval is invariant? We can again start with two spacetime intervals measured in two different frames. Let's assume that ds squared unprime is equal to some function of space, time, and speed times ds squared prime. That's the most general case. There's only a few ways this function can work. Again, it can be a function of position, orientation, or speed, and its orientation. To start with, let's ask some questions about space and time. Does space itself vary from place to place in any given inertial frame? are space distances lumpier here and smoother there? It seems like an odd thing to ask or even to state. So let's say that space itself doesn't vary from here to there, no matter your inertial frame of reference. That's nice because you might not run into a wormhole or a toroidal spacetime or multiply connected spacetime with holes like Swiss cheese. And this means we'll assume that space is homogeneous. Therefore, our putative function cannot be a function of position, and it doesn't matter where you set up your inertial reference frames in space. Every spot is just the same as all the other spots. Next, what about the orientation of our reference frame in space? This too sounds odd. Why would it matter which way we chose the x-axis to be? Therefore, we can assume that space and its distances are also isotropic. We wouldn't get different meter stick measurements if we pointed it up versus pointing it to the left, so our function can't depend on the orientation of the relative motion either. We can whiz by anyone from any angle and still get the expected Lorentz transformations. This leaves our little function with only a function of the relative speeds of the two inertial reference frames. To see why this doesn't matter, let's create two more reference frames. We have two, why not four? Now, each of these is moving at a constant speed, but all of them are oriented differently from each other. Well, now we're in unprime, and to go from k1 to us, we need a to be a function of v1 only, k1's relative speed to us. k2's a only depends on its relative speed to us as well, v2. Now, if we go then from k2 back to k1, that must only also depend on their relative speed, v1 too. All right, now we have two ratios that must be equal, because if you equate the first two equations, you get our home ds squared. You get AV2 over AV1, which is now must be the same as AV of 1, 2. Looking at the left side, the ratio of AV1 over AV2 only depends on their individual speeds with respect to my unprimed frame. So there is no directional component. It's just a comparison of speeds. But on the right, AV12 will always depend on the orientation of K2's movement compared to K1's movement. That right-hand side can vary between 0 and, say, the sum of their relative speeds, but the left is a constant ratio. The only way for them to be equal, which they must be, is for the helper function a to be exactly 1. Therefore, the spacetime interval is invariant. Not the passage of time, not the physical size or distance in one frame, but the peculiar combination of space and time that shows up in the intervals across the top. And this is what we mean when we say that space and time are intermingled and must be thought of as a unified object called spacetime. We will, for all cosmology, apply the idea that the spacetime interval is invariant measure of distance, no matter your frame of reference. Now, the previous slide was all dependent upon our assumption of the Copernican or the cosmological principle, that the universe is homogeneous and isotropic. This principle has enormous evidentiary support from lots of astronomical observations. If you'd like to learn more about that, go back and watch the chapters 1 and 2 of this series. Also, if you want to learn more about special relativity, watch my series in my Introductory Astronomy modules on general relativity. I go into some great detail there. Even though special relativity is incredibly important, we're going to say goodbye to it as we go into general relativity and cosmology. But special relativity has some amazing things that we just want to touch on here. Observers in mutually moving reference frames will see each other's clocks running slowly. They would also see each other's clocks set up in the frame's grid to be out of sync. Of course, each observer would of course see their own clocks running just fine and completely in sync. And because of that, something that's simultaneous in one frame will not be observed to be so from the other frame. This is the source of the barn door and relativistic pole paradox. Further, they don't even measure the same lengths of objects. Each sees each other's objects foreshortened in the direction of motion. But the observers themselves always see their own frame as just fine and not squished flat. To take one example, time dilation itself, it can actually be pretty easily studied and understood. Muons are created in the Earth's upper atmosphere when cosmic rays strike atoms at relativistic speeds. These muons have a very short lifespan, so short that they're literally not going fast enough from a classical perspective, to make it to the ground before they decay. But they are seen to make it to the ground. How is it possible? We see the muon traveling very fast compared to our frame of reference, so we observe its clock slowing down. Well, that's all well and good, but that effect is symmetric. The muon sees our clock slow down too. That sounds bad because now it sounds like it's going to take even more time. But the situation is saved because of the special relativistic length contraction. The Earth's atmosphere and the mountains all look flatter to the muon. The height is foreshortened. So to the muon, the distance is very short. So short that there's more than enough time to get to the ground. And the crazy thing is, this has been measured. And if you add in mechanics and moving masses, you get Einstein's famous E=mc² equation. And we also learned that massless particles move only at the speed of light. They can't not. This also means that all particles of any kind cannot go faster than the speed of light. And if you want to learn about temporal paradoxes due to special relativity, see my video on tachyons and tacos. Well, that was quite a journey. I'm glad you stuck with me for this hour on special relativity. We covered quite a lot of material, but it's just worth repeating the core tenets of Einstein's work. Special relativity arose out of the crisis between three pillars of classical physics: Galileo's relativity, Newtonian mechanics with absolute space and time, and Maxwell's equations that demonstrated all electromagnetic effects travel at the speed of light. This led to the serious search for the luminiferous ether, the medium in which light travels, which was then met with abject failure. To account for this, Einstein threw out absolute space and time and raised the speed of light to a fundamental universal constant that acted merely as a conversion factor between space and time, or possibly not considered a speed, but rather how space and time combine to become spacetime. With that, questions like how far is a nanosecond? What's the span of time between two sides of a river are actually sensible. Finally, in four-dimensional spacetime, we measure true distances using the invariant spacetime interval. Well, now this isn't the end of relativity. Next time, we'll see how Einstein's ideas play out in the presence of gravity and how he reconfigured the entire concept of gravity into geometry. If you like this video, please like it, please share it, and please subscribe. Also, consider becoming a Patreon member or becoming a YouTube subscriber. That support goes a long way to help me make these videos. See you next time. Hello, I'm Jason Kendall, and I've been going through Dr. Barbara Ryden's textbook, Introduction to Cosmology. This is Chapter 3, Section 3, The General Way of Einstein. I'm glad you're watching, and I'd like to take a moment to acknowledge my Patreon supporters and my YouTube members. Their support means a lot to me, since it does keep this channel going. And if you like what's been happening on this channel so far, please consider joining up. I also give special perks and advanced views to my supporters. And now on with relativity. Specifically, how did Einstein geometrize gravity? And where did that idea come from? Previously, I described the successes of special relativity. However, its true usefulness can be seen to be quite limited. It only applies in situations where gravity is non-existent. Now, Einstein knew this, and so he struggled for a decade to extend special relativity into the realm of gravity. In 1907, he discovered that if you have two apparently quite different measurement frames, one subject to a constant gravitational field causing acceleration, and the other subject to a constant acceleration, such as a rocket far away from any gravitational field, identical physical laws are observed in both frames. His version of the Newtonian Equivalence Principle that was consistent with special relativity meant that because the physical laws in both frames are the same, Einstein assumed that the gravitational field and the acceleration were physically equivalent. And Einstein stated this as a hypothesis in 1907, we assume the complete physical equivalence of a gravitational field and a corresponding acceleration of the reference system. Then in 1911, Einstein used his equivalence principle to predict that clocks run at different rates in a gravitational potential and light rays bend in a gravitational field. This connected the equivalence principle to his earlier principles of special relativity. This assumption of exact physical equivalence makes it impossible for us to speak of the absolute acceleration of the system of reference, just as the usual theory of relativity forbids us to talk about the absolute velocity of a system, and it makes the equal falling of all bodies in a gravitational field seem a matter of course. After his successful integration of special relativity into the mathematical framework of differentiable Riemannian manifolds in 1915, Einstein recalled the role of the equivalence principle. The breakthrough came suddenly one day. I was sitting in a chair in my patent office in Bern. Suddenly, a thought struck me. If a man falls freely, he would not feel his weight. I was taken aback. This simple thought experiment made a deep impression on me and led me to the theory of gravity. The equivalence principle underpins the entire concept of the modern conceptualization of gravity, that it is not a force, but rather a curvature of spacetime that is intrinsic to spacetime. This is different than the idea of an extrinsic curvature, where you have, say, a cylinder in space. The cylinder itself on the surface has no intrinsic curvature. And if you're riding around on the surface, you can do all of Euclid's axioms for a flat surface. To show that this is true, just remember that a cylinder can be made very easily by taking a flat sheet of paper and curling one edge around to the other side. Therefore, on the sheet of paper, you haven't changed anything. You've simply taken the paper and connected one side to the other. That still is intrinsically flat on the surface. Now, of course, it's been bent through the third dimension of space. That doesn't really matter here. If you see the cylinder from above or away from it, then of course the surface is curved around. This distinction is important for the concept of general relativity, but the intuition for this arises only out of studying and internalizing the very important core idea of the equivalence principle. Today, we speak of the 3 different versions of the equivalence principle, and I'll go over each and give some examples. Then I'm going to discuss some of the modern tests and finish up with a brief description of what we mean by straight lines in a curved spacetime. First, let's go back and look at Galileo's and Newton's version of the equivalence principle. In my previous video titled The Way of Newton, I went into some detail about this, including current tests around it. We'll now take a refresher in what's called the weak equivalence principle. Let's reach back to when Galileo compared different materials experimentally. He determined that the acceleration due to gravitation is independent of the amount of mass being accelerated. To be fair, he didn't call it gravity. He made observations about falling and rolling objects. Sometime around 1590, Galileo Galilei, while he was a professor of mathematics at the University of Pisa, was said to have dropped unequal weights of the same material from the Leaning Tower of Pisa. Being a generally grumpy guy, he wanted to disprove Aristotle's theory of gravity. Aristotle wrote that objects fall with a speed proportional to their mass, and Galileo was nearly certain it was false. Primarily, Aristotle hadn't done any actual experiments, but just logicked it out. To accomplish this weighty defenestration, Galileo wanted to show that the time it took for different weights to hit the ground was independent of their mass. Perhaps they were 2 differently massed iron balls, perhaps something less destructive to the pavement below, we don't really know. In any event, according to the story, Galileo saw that they hit the ground at nearly the same moment, and judging by the sounds when they hit, that they'd accelerated in their fall, and further, that they fell with the same acceleration. This proved his prediction, and at the same time disproved Aristotle's theory of gravity. This was one of the many things Galileo did to upset the apple cart. He had hypothesized that the distance covered by a falling object is proportional to the square of the time elapsed since it was dropped. And in 1604, Galileo successfully measured this very acceleration of falling objects using the timing of his heartbeat. The result was published in The Two Sciences in 1638. In the same book, Galileo suggested that the variances of the speeds of falling objects of different mass was due to air resistance, and that objects would fall completely uniformly in a vacuum. And that's what we're seeing Apollo astronaut David Scott test on the moon back in 1971 with the hammer and the Falcon feather. Just 50 years after Galileo, Newton developed the differing concepts of gravitational and inertial mass. He then compared the periods of pendulums composed of different materials to verify that these masses are the same. His discovery became known as the weak equivalence principle. The weak equivalence principle, also known as the universality of freefall or the Galilean equivalence principle, can be stated in a quite detailed language as follows. All uncharged, freely falling test particles follow the same trajectories once an initial position and velocity have been established. Further, in a uniform gravitational field, the acceleration of each test particle is completely independent of its properties, including rest mass and composition, and finally, each test particle falls with exactly the same acceleration. I described this at length in the first video in the chapter of The Way of Newton. It bears repeating that in order to make this statement, Newton had to assume that forces arise from everyday actions like lifting things off the ground, pushing things across a table, and launching a rocket with chemical explosives are all due to natural forces. The inclusion of gravity as a force with no discernible means of action was greatly troubling to Newton. Going back to his statement, which was a core of his finding in his 1687 masterwork, Philosophiae Naturalis Principia, mass and weight are locally in identical ratios for all bodies. It's also important to note that this caused a lot of consternation in the world of science. Here, we see the origin of the idea that gravity is a force to be put on equal footing with the force a horse exerts while pulling on a carriage. This way of thinking also draws on the idea that objects are held together by some intermolecular forces and not gravitationally. The freely falling objects discussed using the weak equivalence principle are bound together by non-gravitational forces. This would apply to apples and oranges and to boulders and feathers. In sum, the weak equivalence principle merely states that all objects fall at the same rate in a gravitational field regardless of their mass. The Einstein equivalence principle states that inertial and free-falling systems are entirely equivalent. In such laboratories, there is no experiment of any kind that is capable of distinguishing between inertial and free-falling motion. This is because the Einstein principle of equivalence declares that the acceleration of a free-falling laboratory completely cancels out the effect of gravity, not only dynamically, as in the weak equivalence principle, but also in any conceivable experiment in any branch of science. Therefore, special relativity, and not just Newtonian mechanics, may then be used in free-falling systems as well as inertial systems. There are only a few limitations to the Einstein equivalence principle. Well, the main one is that the experiments conducted can't be ones that involve self-gravitating properties. We'd need to test electromagnetic interactions or, say, the weak nuclear force interactions. Indeed, one main motivation for the Einstein equivalence principle, or just EEP, is in trying to integrate the theory of electromagnetism into the framework of gravity. So let's get into the details on this. What is now called the Einstein equivalence principle states first that the weak equivalence principle holds. Then, to complete his work on gravity, Einstein included two more ideas into his form of the equivalence principle: local Lorentz invariance and local positional invariance. Local Lorentz invariance means that no matter how the experimental laboratory is freely falling with respect to the ambient gravitational field, inside the laboratory frame, all experiments done in that frame will be measured as in an inertial frame. In other words, the outcome of any local non-gravitational experiment is independent of the velocity of the freely falling reference frame in which it's performed. This is exactly like being down in the hold of Galileo's boat. Now, in addition to sailing on a glassy sea at constant speed in one direction, we can now surprise poor Galileo by dropping his boat from a great height or sending him flying into space in orbit around the moon. Such a spacefaring, freely falling Galilean boat might have floating fish and water droplets hovering stationarily in the air, or, as we see Commander Scott Kelly aboard the International Space Station, one can juggle balls by simply placing them where you want them to be. they'll just stay there because they're simply falling at the same rate as everything around them. But as the ISS goes around the Earth at 90 minutes per orbit, it experiences changes in the gravitational field. Other than the tiny effects due to non-uniformity of the gravitational field, Commander Kelly's experiments aboard the ISS are a nearly perfect inertial reference frame. The speed, altitude, and direction of the ISS through the Earth's gravitational field doesn't affect, except at tiny levels, the fact that it's fully equivalent to the ISS being deep in space, far away from any gravitational field whatsoever. In many ways, the concept of local Lorentz invariance is essentially where special relativity gets integrated into general relativity. It's truly astounding the scale and amount of experimental support for special relativity that has led it to being central to all physics. The vast supporting experimental evidence for the local Lorentz invariance includes, of course, the classic Michelson-Morley experiment, and tests of time dilation by Eves and Stilwell and Rossi and Hall, tests of whether the speed of light is independent of the velocity of the source, using both binary X-ray stellar sources, where the source of photons is coming from an accretion disk around a stellar mass black hole, and secondly, high-energy pions impinging on the Earth's upper atmosphere and cosmic rays. There are also numerous tests of isotropy of the speed of light, which would of course violate local Lorentz invariance. In addition to these direct experiments, advancements in quantum mechanics have cemented local Lorentz invariance via special relativity's integration. Specifically, Dirac's equation predicted antiparticles and quantum spin, which then spawned the stunningly successful relativistic theory of quantum electrodynamics. In 2024, 119 years after the introduction of special relativity, it is actually safe to ask what is there left to test. Special relativity, and therefore local Lorentz invariance, has been so thoroughly integrated into all modern physics that its validity is rarely challenged except by cranks and crackpots. Interestingly then, since the early 2000s, legitimate theoretical and experimental efforts have been undertaken to find violations of special relativity. This is because the promise of quantum gravity theories is to seek new physics that extends Einstein's relativity. This doesn't mean relativity will be replaced or invalidated, but it means that new interactions yet unseen remain to be revealed. Such models predict apparent or effective violations of Lorentz invariance. Quantum gravity, in general, asserts that there is a fundamental length scale given by the Planck length, which is 10 to the minus 35th meters. But length is not an invariant quantity due to special relativistic length contraction. So there might be something there to seemingly violate local Lorentz invariance. Next, in a brane world, with our universe embedded in some higher dimensional bulk, like we saw in the movie Interstellar, the confinement of normal physics interactions to our four-dimensional brane could induce apparent Lorentz violating effects for us, while leaving it locally invariant in the higher dimensional bulk world. And finally, string theory or M theory suggests effective or apparent violations due to the existence of new and additional scale, vector, and tensor long-range fields, which couple to the normal matter. This last one's getting way ahead of ourselves, though. Let's now look at local positional invariance. This means that no matter where or when in the universe we put our laboratory frame, there won't be any difference between the frame's measurements. This has huge implications for physics. One of the most important results is that the physical constants of nature, such as Newton's gravitational constant and the fine structure constant, are not functions of space and time. They don't change. This means they are profoundly elemental to the physics of our universe. Of course, this is going to lead to some very interesting tests, which I'll talk about later. Here, the local in local positional invariance and local Lorentz invariance means that the experimental setup in the laboratory must be small compared to variations in the gravitational field. These, of course, would be the tidal forces, and the test experiment must be small enough so that the gravitational potential does not alter the result. Just adding the constraints of local Lorentz invariance and local positional invariance, Einstein was able to predict the gravitational redshift, which has subsequently been observed. Theories of gravity that obey the Einstein equivalence principle are forced to be what we call metric theories of gravity. Such theories mean that all freely falling bodies follow trajectories that are things we call straight lines in curved spacetime, geodesics. I'll get into the definition of a geodesic later on in this video, but suffice it to say that it's the shortest distance in a curved spacetime. So to recap so far, the differences. In the weak equivalence principle, we have that the inertial mass and the gravitational mass of any object are equal, or equivalently, in small enough regions of spacetime, the motion of freely falling particles in a gravitational field are identical to motions in a uniformly accelerated frame. In contrast, the Einstein equivalence principle states that, in small enough regions of spacetime, the non-gravitational laws of physics reduce to those of special relativity, and it's impossible to detect the existence of a gravitational field by means of local experiments. Gravity, then, couples not only to rest mass, like the Leaning Tower of Pisa of Galileo, but also to all forms of non-gravitational energy and momentum, such as the electromagnetic binding energy of atoms and molecules, and makes any experiment useless to test the difference between an inertial frame and a freely falling frame. And now let's see how we can take it a step further. The strong equivalence principle applies the same constraints as the Einstein equivalence principle, but allows the freely falling bodies to be massive gravitating objects as well as test particles. Thus, the strong equivalence principle applies to objects that exert a gravitational force on themselves, such as stars and planets, black holes, and Cavendish experiments. I alluded to some of the results of this just a bit ago as part of the Einstein equivalence principle. This does make it a bit fuzzy between the two, and clarifying exactly what a non-gravitational experiment truly is does come up as a matter of debate among physicists. For this purpose, the strong equivalence principle, in order to have gravitational interactions explicitly obey the universality of freefall, local Lorentz invariance, and local positional invariance, creates the strongest possible restrictions on theories of gravity. Namely, the strong equivalence principle requires that the gravitational constant be the same everywhere and every when in the universe. The SEP then says there are no other forces other than what we've already discovered. There would only be gravity, electromagnetism, the weak nuclear force, and the strong nuclear force. These are the only allowed interactions of matter, and this is the standard model. That's what we mean by the statement that the strong equivalence principle is incompatible with a fifth force. Like the Einstein equivalence principle, the strong principle requires gravity to be geometrical in nature, but in addition, it forbids any extra fields. Therefore, the metric alone determines all effects of gravity. Why? If an observer measures a patch of space to be without curvature of any kind, then the strong principle suggests that it is absolutely equivalent to any other patch of flat space elsewhere in the universe, and elsewhen in the universe. Matter in all flat spaces in the cosmos for all time behave and interact in exactly the same ways. Einstein's theory of general relativity, even including the cosmological constant, is thought to be the only theory of gravity that satisfies the strong equivalence principle. There do exist a number of alternate theories, such as Brand's-Dickey theory and the Einstein ether theory. These theories add additional fields and state that the metric is not the sole determining factor in the free-falling movement of matter in spacetime. Also, like I stated earlier, grand unified theories that combine electromagnetism, the weak nuclear force, and strong nuclear force with gravity in some way, as well as quantum gravity theories, all require additional fields in order to couple spacetime itself to phenomena that would then eventually violate local Lorentz and positional invariances. For the rest of this course on Ryden's Introductory Cosmology, we're going to work inside a physics framework of the strong equivalence principle. Amazingly, that's all we'll need for almost all studies of the universe that track its evolution and fate from here to the wildly unforeseeable future. It also takes us all the way back to the first tiny fractions of the first second of the universe's existence. It also works for more mundane things like your GPS system and local satellite orbital mechanics. Adding in quantum gravity to our study of classical relativistic cosmology will only get muddled by such considerations. However, once we get into the realm of the inflationary epoch and inside the first second of the Big Bang, we will need to return to this topic again. In general, for everything we'll encounter in cosmology, we'll likely use the strong equivalence principle. A big caveat is, of course, the current debate over the Hubble tension. This may promise to see violations of the strong equivalence principle by introducing new physics evident in the observation. But that's for another day. For now, let's look at a bunch of examples and thought experiments about the equivalence principle so we can get a good feeling for what it means. First, let's look at the basic idea that Einstein used to develop the concept of gravity. His great insight was, a falling man does not feel his own weight. As you can see from this diagram, you've got a man, and he's in a box, which happens to be a room or laboratory. And he's floating in space. He's freely falling inside this box with everything else, all falling at the same rate towards the Earth, or if he's deep in space, far, far, far away from everything. These two situations, according to Einstein's equivalence principle, are exactly identical. We will call them free-falling or inertial frames, and we're going to justify that later with many examples. Next, to see the effect of Einstein equivalence principle, let's take this guy and put him in a deep space. He's got his laboratory, and inside this laboratory, floating far from anywhere, he's pointing a laser across the lab at the far wall. In addition, there's some magnets at rest. These will, of course, make no electric currents in nearby conductors unless he starts moving the magnet around. Further, observations of atoms and molecules from chemistry experiments or spectroscopic measurements will not experience Doppler broadening or any redshift or blue shift. Nuclear processes behave as they do in any laboratory at rest. They'll just behave normally. Well, as normal as it is to be floating out in space far away from any gravity. And finally, let's say we have two balls of the same mass, but different compositions. They're just going to float there, maintaining their relative positions. This would also be true if they're made of the same stuff, but of differing masses. As the experimenter does more and more thorough experiments, he or she would discover that the laws of special relativity hold in the laboratory for all experiments, because at this point, they're far, far away from any gravitational fields. So any small-scale laboratory test that involves speeds close to that of light will show time dilation, length contraction, and clock desynchronization. This is exactly what is known from special relativity, which I talked about previously. But now, sometime later, the lab drifts closer to some star and gets caught in its orbit. The lab begins to fall freely around the star, changing speed as per Kepler's laws, speeding up when it gets closer and slowing down when it gets farther. Since the lab is small with respect to the gravitational field, or if the gravitational field is not extremely strong and there are no windows, the experimenter will not be able to tell that they're in orbit. They're freely falling around the star. It'll be just the same as if they're floating out deep in space as before. There'll be no experiment that will be able to show that they're in orbit around a star. And of course, I'm ignoring the non-uniformity of this gravitational field. There will, of course, be tidal forces due to that. But removing that, we can make the orbit large, like the size of Jupiter's orbit at about 5 astronomical units. That should do it, unless, of course, the lab then falls towards Jupiter or whatever. In general, though, in a locally uniform gravitational field, our intrepid experimenter or trapped experimenter doomed to work alone in a windowless box will still think they're out blissfully deep in outer space. Let's look at one experiment on board. A laser. In both instances, we see the labs are freely falling. In both cases, we say they are in inertial reference frames and the laser goes across the room in what the experimenter measures to be a straight line. On the right, deep in space, far away from any gravitational source, he shoots the laser across and it hits the far wall straight. The same will happen if you're freely falling in the Earth's gravitational field. This works for any orientation due to the local positional invariance. Of course, there will be a change due to the inevitable quick and abrupt stop for the person on the left. Other than that, there's no way to tell whether you're falling in a uniform gravitational field or a truly freely falling Lorentz frame. Things are different when you start on the ground. This is the classic example of the Einstein equivalence principle. The person inside this closed room will feel their weight as they stand up. Apples will fall with 1g acceleration towards the ground. The person will also feel a weight of 1g if the lab is in a rocket accelerating upwards at 1g acceleration. This assumes that our rocket starts accelerating in deep space far away from any planets or stars, and that our experimenters slept through the engine ignition or whatever magic transformed the entire Earth into a rocket in a blink. Given continuing silencers on the rocket, there would be no difference in the effect of the acceleration of a rocket versus the weight of standing on the ground on the Earth. This has interesting consequences. Let's say now you're deep in space, and we'll imagine two observers looking at the same event. One observer is weightless, floating only on a space station and only standing there because of magnetic boots or something. The other is more safely in a rocket, accelerating upwards past the station. Inside the rocket, there are 3 apples suspended in a row. The space station observer, let's call him Stuart. Stuart sees them in a straight line, which just so happens to line up with some batons. And he has this magical thing with the batons where he lets them go and to do whatever they're going to do. But initially, they're lined up with the batons. The rocket observer, let's call him Elton because he's a rocket man, sees them start off in a row as well, at the top of the box of the rocket. As the rocket accelerates upwards, the batons release their magical hold and the apples are allowed to move freely. Note that this is in deep space, and the rocket and space station do not have enough mass to be significant gravitational bodies. Let's now say that the 2 leftmost apples stay put, but let's say that the rightmost apple is given a tiny shove when the batons let go. Now, all 3 apples are free to move and don't have an initial velocity, and one is moving to the right at, say, a foot per second, a constant speed. Let's see what happens. First, we note that Elton feels his weight as the rocket accelerates, and Stuart stays floating. Well, he would float off if his mag boots turned off, but he is floating along with his little space station. The apples, according to Elton, appear to be falling towards the floor, but according to Stuart, they're staying in a line with the magic batons. Both see the rightmost apple drift further rightward. The rocket accelerates and picks up speed. Stuart still sees a straight line, but Elton sees them falling faster. Lastly, they hit the floor because the rocket has accelerated up to meet them. Stuart last saw them just before they splattered on impact as still in a straight line, which is what he saw the entire time. But now let's look at a summary of all these steps. As you can see, according to Elton, inside the rocket, the apples fell and the rightmost one traced a parabolic curve downward. This is just like on Earth if you throw something off a ledge. Now let's assume the rocket was accelerating at 9.8 meters per second squared and that the rocket's windows are closed. As per the weak equivalence principle, Elton couldn't tell if he was on Earth or in a rocket, and that's the essence of this. This comparison shows that there is a complete equivalence of the 2 non-inertial, non-free-falling accelerated reference frames. On the left side, it's a rocket-accelerated frame, and on the right side, it's a gravitational field. And there's no way to tell the difference, and this is the weak equivalence principle in action. There's no difference at all between inertial mass and gravitational mass. Let's now see the effect on something that does not have mass. And let's go back out to Stewart Space Station. They got good coffee and croissants out there. We reset the test, and now the batons line up with the nozzle of a laser gun. This laser gun is fixed at the top of the rocket's hold so that no one gets zapped by the beam inside the rocket. Stewart's batons will make the laser gun fire just as Elton's rocket accelerates on by. While it's in flight, it is not attached to the rocket anyway, so the laser will travel in a straight line along the lines of the batons. Without the rocket there, the laser would go from one baton to the other. One could even imagine, instead of a rocket, a cable pulling up the laser gun with a constant acceleration changing its speed. The laser bolt is not attached to the gun or the rocket in this case. Now let's consult with Elton and see what he measures again. The rocket accelerates upward as the laser bolt moves across the rocket, and the rocket rises up to meet it. The rocket goes faster, even as the laser bolt's speed stays the same, moving towards the other baton in a straight line. Finally, the bolt hits the other side of the rocket by Elton's feet. Stuart, though, is unsurprised. To him, it just went in a straight line. But Elton sees something alarmingly different. First, Elton is a bit annoyed with Stuart and his dangerous batons making laser guns shoot inside his rocket, but also the laser bolt bent downward in the rocket's cabin. Now, if instead of a bolt, it were a continuous laser and the rocket kept its acceleration, then the downward bend would be visible as a beam. If Elton starts to decelerate, this laser will, of course, point upward. Finally, if Elton stops or maintains a constant speed, the laser will, of course, now look like a straight line, just like it did to Stuart. It is the acceleration that is changing the laser's path. But by the equivalence principle, and you knew this was coming, the equivalence principle states that the same thing would happen on Earth in a uniform gravitational field. Light's path, therefore, will be bent by a gravitational field in exactly the same way as if it were in an accelerating reference frame. There is no difference. Now, light is photons, and photons have no mass, yet here they are being deflected by gravity, which would quite surprise Newton. The force of gravity, as he envisioned it, is between two masses. It should only affect masses, but light is deflected even though it has no mass. This effect was predicted by Einstein, and it was subsequently observed by Sir Arthur Eddington as he observed the change in the position of stars during and after a total solar eclipse in 1919. Stars that were visible near the limb of the eclipsed sun were observed to be displaced compared to their positions when the sun was far away in the sky. Eddington and his team looked at them well before the eclipse and carefully mapped their positions. Comparing the images of the positions before and during the eclipse clearly showed Einstein's predicted deflection. So this is a measured and measurable real effect. Getting back to Stewart and Elton, since we know that Elton's laser made a straight line as seen in an inertial observer's frame, we must conclude that this bent path is the shortest distance for the laser to travel in the accelerated reference frame. Elton and Stewart would, if they could, count exactly the same number of wave crests of the light of the laser beam. As for their wavelengths, Stewart would see them unaltered, would measure them to be unaltered, but Elton would measure them getting shorter as the rocket accelerated. Elton and Stewart both agree that the light has the same speed, and no measurement will tell them otherwise. But Elton will be forced to admit that the shape of straightness is different for him than for Stewart on his magnetic space station. Elton's straight is bent. We are forced to admit that this path is a straight line in both the accelerating rocket and standing on the globe of the Earth. This can only mean that space-time on which light is riding is curved in such a way as to bend the path down towards the acceleration or down gravity slope. Also, in both frames, the total space-time distance is the same for Stewart's measurement from the station or inside Elton's rocket. Specifically, because it's light, that path has a null space-time distance. Therefore, some combination of length contraction and non-uniformity of clock time in these accelerating labs must occur for the speed of light to be a universal constant for all observers. And this is what we mean by curved spacetime. Now, let's look closer at how clocks tick inside the rocket because of that non-uniformity of clock time. Once it became accepted that light was an electromagnetic wave, it was clear that the frequency of the light should not change from place to place inside an inertial Lorentz reference frame, because waves from a source with a fixed frequency will keep that same frequency everywhere, unless they change media, like space to water or space to air. But what if time itself were altered and clocks at different points in spacetime ran at different rates? In 1917, this is precisely what Einstein concluded would occur in an accelerating box. Here we're going to use the rocket again with Elton in it and work with the special theory of relativity. We'll check the clock rate at the bottom of the box, i.e. the side away from the direction of acceleration. Now we check the tick rate on the side towards the direction of acceleration, that is, the top. Let's call up direction x in a frame moving in the x direction with a velocity v relative to some rest frame. For this rest frame, we'll use the bottom of the rocket. Now we check the clock at a nearby position upwards, dx. So to a first-order approximation, t sub dx is about equal to dx over c times v over c. That's what you get by looking closely at the Lorentz transformation we see above, letting t tick be the time a little bit higher up than the lower clock's time t. Now we take into account the acceleration g, which would change the speed by g times dt. Here, dt is a little change in the clock on the floor. This makes the clock at the position a little bit higher to be ahead by dx over c times g over c times dt. Looking closely, we see these stacked up clocks have different tick rates. The tick rate r, a little bit higher up in the rocket, is slower by g over c squared times dx, where dx is the amount of distance a little bit higher up in the rocket. The equivalence principle implies that this change in the clock rate is the same whether the measured acceleration g is due to an accelerated frame without gravitational effects, like a rocket, or caused by a gravitational field in a physically stationary laboratory. Yes, that means clocks high up in orbit around the Earth run slower than those on the ground. And this has to be taken into account for GPS satellites. If it weren't, the satellites would be wrong by a meter within minutes, and they'd be off by miles very soon thereafter. Because of this clock slowdown, Einstein predicted that a uniform gravitational field would also cause a redshift. The laser is emitted as blue light at the bottom from our laser gun, and is redshifted by the time it gets to the top as the rocket accelerates. Again, this is Elton going by Stewart, and Stewart keeps saying, okay, when you finally get done showing off, let's have a hamburger. The station's burgers are made with bison and elk. And as the rocket accelerates, the top recedes away from the approaching laser, eventually crossing the distance from bottom to top. Another way of analyzing is from Stewart's perspective. Here, the spatial distance is much greater between the batons. And because it's a laser, the space-time difference in both frames is identical, specifically 0. This means that both Elton and Stewart will count the same number of wave crests traversing the distances they see. Elton's is a non-inertial accelerating frame, and Stewart's is an inertial Lorentz frame. This all means that the frequency of the laser must decrease so that it traverses a shorter distance. This frequency change lengthens the wavelength, making the effective space inside the rocket larger. Therefore, when the laser reaches the top, it's going to be stretched out in its wavelength. Remember that both observers will measure exactly the same number of wave crests and therefore events in the laser in their detectors. The accelerated non-inertial observer will measure a laser that has a lower frequency at the top than compared to the bottom. And by the equivalence principle, this is exactly the same as what would happen in a gravitational field. So now let's depart from these thought experiments and examine a real-world experiment that doesn't involve rockets and closed rooms. Imagine you take a ball and drop it from a great height. When it hits the ground, it will have acquired energy from its fall, specifically mgh, where m is the mass of the ball, g is the Earth's gravitational acceleration, and h is the distance fallen. If you add this energy to the rest mass energy of the ball, mc squared, you get the total energy of the ball as it's fallen. Now, let's say we have a magic box that transforms all the energy of the ball, rest and kinetic energy from the fall, into a single photon with an energy h nu, which then rises back towards where the ball came from. A receiver magic box at the top of the tower then converts all of this photon's energy into the rest mass of a new ball, and this new ball has more rest mass because it has acquired that new energy from the fall mgh. So now, if you put this in a loop, you'd have a perfect perpetual motion machine. And since we never really like the idea of getting something for nothing or your kicks for free and find the perpetual motion generally bad, the best we should be able to hope for is the simple recovery of the original ball with mass m and rest energy mc squared. This means that the energy of the photon received at the top, h nu tick, must be less than what it had when it was created at the bottom. This energy loss from bottom to top is roughly gh over c squared. This was Einstein's original reasoning that led him to know that there must be some kind of energy loss as photons rise out of a gravitational field. This is an excellent example of the Einstein equivalence principle at work because it explicitly uses the electromagnetic radiation in a lab setting rather than just masses freely falling. Then came along the Mossbauer effect. In 1958, Rudolf Mossbauer, while spectroscopically analyzing a gamma-ray nuclear transition of iridium-191, discovered that if he cooled the emitter down to 90 Kelvin, then the nuclei would not recoil when they emitted such high-energy photons. This recoilless gamma emission allowed another iridium-191 nucleus in a distant detector to absorb the photon in a resonant manner, completely absorbing the photon into the nucleus and going into an excited state. This had never been observed before. because the recoil is usually so large that the gamma ray is Doppler shifted on emission to be the completely wrong energy to excite a distant iridium-191 nucleus out of its ground or unexcited state. With this process, if you wanted to check for the absorption at a frequency just a little bit higher or lower than the resonance, then you have to find some way of moving the detector either towards or away from the source at a speed that would make a Doppler effect to the desired amount. In 1959, Harvard's Robert Pound and his graduate student Glenn Rebka devised a plan to use the Mossbauer effect to measure the very tiny gravitational redshift that should occur as a photon rose up 22.6 meters from the bottom of a tower to the top. To get this Doppler shift, they used an audio speaker magnet to vibrate a sheet covered in a material that could receive the photon. Many materials were shown to be able to do recoilless gamma emission by this time, so Pound and Rebka chose iron 57. It was easy to use and didn't have to be cryogenically cooled. By 1960, they were able to measure this very tiny shift, 5.1 times 10 to the minus 15th, thus proving the Einstein equivalence principle. In 1964, Pound and his colleague Snyder made great experimental improvements, raising the precision from 2 decimal places to 70 parts in a million. Here, we see that the formula shows how small that shift should be. 9.8 meters per second squared times 22.6 meters divided by 3 times 10 to the 8th meters per second squared, which is on the order of 10 to the minus 15th. This begs the question, is there a setup on Earth where the redshift will not occur? That is, can we use a special relativistic Lorentz inertial frame on Earth? Let's see if we can find such a frame. First, let's pretend initially that one does in fact exist. To help us, we use a special relativistic spacetime diagram. Time ticks going up the vertical axis, space is going higher to the right. That's normal for spacetime diagrams, don't fret it. What we really want to know, though, is could there be any frame where the frequency does not change? Here, we're assuming that in this diagram, we found one. So let's see how that works out. When the photon is emitted, it's a packet of waves, or a wavelet. It will have crests of the waves inside of a single photon. There will then be some tiny interval of time between successive crests of the photon's wave packet. In such a frame, as the photon rises up to the top of the tower, left to right in this diagram, gravity can be doing any old thing. But the first wave crest travels the lower green line, and the second wave crest travels the top one. Now, as the photon rises along the way, gravity might do something to it, but gravity is not time variant along this path. Therefore, both paths will be affected in the same way on the same trip. The green lines are made deliberately goofy because we don't want to make any assumptions of what gravity might look like in this region. But both wave crests will feel it identically in our putative at-rest reference frame. Therefore, when the photon goes to the top in the no redshift Lorentz frame, the tiny time changes between the crests will not change. However, from both the heuristic arguments and Pound, Rebka, and Snyder's work, we see conclusively that the frequency shift up to the top of the tower means that the wave crests have spread out and that the delta t's must change. Therefore, special relativity and Lorentz frames do not apply to the Earth or to any location with a uniform gravitational field. They also don't work if we take into account tidal forces from non-uniform fields. We can do better than a little diagram to demonstrate this mathematically. Using the standard Lorentz transformation of special relativity that I discussed at length in the previous lecture, we can derive the time difference due to transforming from one frame to another moving frame with some constant velocity relative to the original frame. We see at the end that the Lorentz transformation depends on some constant speed to give the difference in the passage of time as measured by clocks in different frames. However, the Pound-Rebka experiment shows that the time difference depends on the height in a constant gravitational field. This means every little height difference would need to be represented by a different Lorentz transformation with a different speed. We're now stuck. We can't just find one Lorentz frame to do it all for the Earth. We have to find a different one for every tiny bit of height difference. What a mess! Okay, so if we can't have a constant velocity frame, what if we created a frame that exhibited a constant acceleration? If we abandon inertial frames and just use some non-inertial accelerated falling frame, then maybe we can do it. And that's what I'm trying to represent by these falling boxes. It's not that one box is the frame, but rather that the reference frame itself is under constant acceleration at a given point. This also helps us remember that reference frames can be simple mathematical constructs that assist in greater understanding, and they don't have to be able to live in reality to be a correct description. Yeah, how would you actually make a frame that is continuously accelerating at a point such that you can put meters and clocks and reference frames in it? That'd be really hard considering that every other second the frame would be crashing into the ground on this particular example. Let's revisit the argument using Lorentz frames, but this time we'll allow the speed of the frame to increase with time. The falling frame starts at 0 speed, with the falling frame and the tower to be matched up. The photon starts at 0 height and will go up to height h. It'll take h divided by c for the photon to get there, and that'll be the time t that we want to know about. When the photon gets up to h, the frame's speed will have increased by g times the time it took for the photon to rise up to height h. Amazingly, comparing the time as measured in the falling frame, t tick, to the time in the tower frame, t, we find that from the standard Lorentz transformation for that moment at that one speed to give a longer t tick. We can remember that frequencies are inversely proportional to time intervals, so nu sub tick is the frequency measured in the falling non-inertial frame, and nu is the frequency as received at the top of the tower. We can mix in the top equation for nu received. We then find that the downward speed of the non-inertial frame creates a Doppler blue shift 1 plus gh over c squared that exactly cancels out the energy loss due to its rising out of a gravitational field. This last approximation arises because that ratio in front of nu emit is like 1 minus g squared h squared over c to the fourth. This is what we call a second order effect. Now the first order effect is small, 10 to the minus 15th, so the second order effect would be about 10 to the minus 30th, so we can safely ignore that as completely unmeasurable. Therefore, we conclude that all effects of gravity on all laws of physics are removed in a freely falling frame. Or, much more specifically, that the Pound-Rebka experiment, to the best of its capability, cannot detect any violation of the assertion of the Einstein equivalence principle's local positional invariance. It's obviously not a test of local Lorentz invariance. We'll chat about more of these tests later. This entire thing is so important, it's worth repeating it. Nu tick is equal to some fraction times nu emit. This fraction is essentially a gravitational blue shift divided by a gravitational redshift. But this ratio is so small that it's practically, in fact, for all intents and purposes, 1. Therefore, the frequency observed at the top of the tower is the same as if it were the one emitted, so long as you're measuring inside of a freely falling accelerated reference frame. And this is what we mean when we say that the Pound-Rebka-Snyder experiment strongly supports the Einstein equivalence principle. There is simply no measurable redshift in a freely falling frame. Within an accelerating, freely falling frame exactly cancels out the immeasurable effects of gravity on all laws of physics. It's just like using special relativity in the absence of gravity. All objects in the freely falling frame, regardless of their composition or charge or nuclear properties, are all unaffected by gravity. All laws of nature will use the framework of special relativity in this freely falling frame. Special relativity is the kinematic framework that is known to be extremely accurate when you have no gravity. In sum, Pound-Rebka-Snyder showed that you can't tell the difference between floating deep in space with no discernible gravity and falling in a uniform gravitational field. Let's now contrast that with our argument about Galileo's boat. That boat was not falling. It was either resting at anchor or sailing straight on a glassy sea, and it's quite obvious that Galilean relativity is much more limited in scope. Galileo and Newton both only considered frames of reference that were either fixed with respect to some absolute time or space, or were purely relative in speed. Both of them considered the effects of acceleration to be the core method of detecting whether or not your observation point was at rest, whether it was a butterfly smashing into the rear of the hold or a cosmically isolated rotating bucket of water. Neither one of them considered the idea that the effects of acceleration could be canceled by measuring while falling along with that acceleration. This was Einstein's great insight while sitting in that chair in his Swiss patent office. This amazing breakthrough is now central to much of modern physics, especially the study of gravity. It's also pretty important to notice that the Einstein equivalence principle says that gravity is actually extraordinarily odd and different among all laws of the universe. The electromagnetic force, you only can cancel that force out by using uncharged neutrons. The weak nuclear force cancels the force by not involving, say, neutrinos or W plus bosons. The strong nuclear force, you can cancel it by assuring nothing interacts with quarks. And particles can be at rest while under the available influence of these forces, so long as they don't involve with neutrinos, or they don't have charge, or we're not talking about quarks. They can be at rest even while those forces are present. But you can't cancel gravity except by freefall. So there's something strange about gravity that says there's something about falling that's really new and different. And therefore, that's why we say that all laws of physics are the same in a freely falling frame and are identical to special relativity when there's no gravitational fields. Gravity is just fundamentally odd and really different. There's no thing that says, let's turn off the charge on gravity. Let's say we have an anti-gravity particle. There is no anti-gravity particle, or there's no particle that says, I don't do gravity. It doesn't exist. That's because all particles follow the shape of spacetime. But before we get into that for just the briefest bit, let's go quickly over some of the huge number of tests of the equivalence principle. In my video on the Way of Newton, Chapter 3, Section 1, I describe in painful detail the tests of the weak equivalence principle, or the test of universality of freefall. The great original was Edwish's torsion balance, which helped determine the value of G. The most accurate one today is the French ESA mission microscope, which found no violation of the weak equivalence principle to 1 part in 10 to the 15th. We also covered the Michelson-Morley experiment, which was hunting for the ether wind, but instead led to the observation of local Lorentz invariance, one of the two beating hearts of the Einstein equivalence principle. Doctor Who fans make some comment here. Modern clock timing anisotropy tests validate the local Lorentz invariance to 1 part in 10 to the 20th. That's an astonishing confirmation. We also went over the local positional invariance test of Pound-Rebka, but others exist, such as a lack of evidence for the change of fundamental constants of the universe in space and time. As for the strong equivalence principle, this is basically a test that G does not change in space or time. It's important to note that most alternative theories of gravity predict a change in the gravitational constant over time, so this is a hot topic of research. For example, orbital variations due to gravitational self-energy should cause a polarization of solar system orbits called the Nordfeld effect. This effect can be and has been sensitively tested by the Lunar Laser Ranging Experiment. Up to the limit of 1 part in 10 to the 13th, there is no Nordfeld effect. Another tight bound comes from modeling the orbits of binary stars and comparing the results to pulsar timing data. In 2014, astronomers discovered a triple stellar system containing a millisecond pulsar that has 2 white dwarfs orbiting it. This study also showed no variation in G either. And the best such data comes from studies of the ephemeris of Mars, based on 3 successive NASA missions, the Mars Global Surveyor, Mars Odyssey, and the Mars Reconnaissance Orbiter. These studies, along with Big Bang nucleosynthesis studies arising from WMAP and Planck, have shown that G cannot have varied by more than 10% since the creation of the universe. These tests are quite extensive, and all have not yet found fault with Einstein's original choices for how gravity should work. That is, gravity is the curvature of spacetime, and all known forces obey this curvature, and further, that there are no additional forces in nature to counteract this idea. We have yet to see if the current Hubble tension will have anything to say that contradicts this, though there is growing consensus it might. In this last moment for this section, I'll touch on something I've alluded to a number of times in the past hour, that the bent trajectories of falling objects and even light are actually straight lines in curved spacetime. Einstein's theory of gravity is one that can be called a metric theory. This means you can create a method to determine total spacetime distance between two events in spacetime. At the top, I'm showing the Schwarzschild metric for a spherically symmetric spacetime centered on a spherical body, such as a star or planet or black hole with mass m. We define some special things like the Schwarzschild radius, r sub s. Mostly, though, this metric states what the total spacetime interval ds is, given changes in time, dt, changes in radial distance from the mass, dr, and changes in rotational orientation around the mass, d omega. We call each of these coefficients associated with the parts dt, dr, and d omega the components of the metric. These are commonly called little g with two Greek letter subscripts. Little g basically describes the shape of spacetime on a point-by-point basis that surrounds the mass m. We can construct interesting mathematical tools out of the metric, such as gamma, which has the formal title of a Christoffel symbol. It's composed of partial derivatives with respect to each of the coordinates of spacetime. This symbol actually represents a large system of equations and encodes the gradient of the spacetime. Just like a topological map of a mountainous hiking area shows a series of points of altitude, the slope or gradient of the mountain at a given point is determined by how close together the lines of the same height are placed on the map. The Christoffel symbols encode the points of the metric into the gradient of spacetime. So what happens when you let something roll down the mountain? For ease, pretend that the slope is free of small rocks and anvils, coyotes and roadrunners, and the ball will go faster and slower down the slope as it encounters the lay of the land. It will also trace a distinct path on the ground, given initial placement and some speed in some direction. At the bottom, we see the geodesic equation of motion for force-free motion through a metric space. The first term is the curvature of the trajectory, which is analogous to acceleration. The generalized gradient term is analogous to a force. Therefore, this geodesic equation is the F equals ma of general relativity. That zero at the end means that all free trajectories follow the principle of least action. This means that the path of freely moving particles, or light, will always be one that minimizes the travel time. In practical terms, this describes a straight path of light rays and the straight path of a box sliding across a smooth, icy lake. A geodesic is the concept of a straight line in curved spacetime. To help understand this, let's go way back to Euclid's axiom that two straight lines that are initially parallel remain parallel whenever extended. Extended is a funny word here. What does that mean? It does not mean continued in such a way that the distance between them remains constant. Euclid means that simply the lines keep going in the direction it was a step before. With this idea, a geodesic is a path described by the geodesic equation that if you now place an arrow at any point on the path and move it along a little bit along that path, it'll stay pointing in the same direction. The crazy thing about this idea is that if you have a flat space, like everyone's idea of 10th grade geometry, and you take an arrow and keep it pointing in the same direction and take it for a walk around a closed loop like a square or a pentagon, then when you get back to the starting point, the arrow will have the exact same orientation as when it started. However, in a curved spacetime, like the Schwarzschild metric, the Christoffel symbols and the geodesic equation combine together to make that arrow change its orientation when it gets back to its starting point. This all means that the downward curvature of the laser in the box is following exactly this spacetime metric. This is pure geometry, but not a geo thing like the Earth, but space and time itself form a manifold that is connected together differently than a flat sheet of paper or cubes or boxes like you worked with in your old Euclidean geometry from high school. Sadly for us, cosmology has no use for this Schwarzschild metric. We only care about the spacetime metric for an isotropic, homogeneous spacetime that is either expanding or contracting or standing still. We'll not need the great and wonderful complexity of strong field general relativity until we take a look at the earliest moments of the universe. Next time, we'll be looking at how Einstein describes curvature in greater detail with a strong focus on this homogeneous isotropic spacetime. Until then, I'll leave you with a succinct summary of Einstein's theory of general relativity by John Archibald Wheeler. Spacetime tells matter how to move, and matter tells spacetime how to curve. Thanks for watching. Please like this video, share it around, and subscribe to my channel. And consider becoming one of my YouTube members or even a Patreon supporter. Giving that support means a lot to me and helps me keep going with all of this material. Well, we'll see you next time for Chapter 3, Section 4, Describing Curvature. Hello and welcome to more cosmology. I'm Jason Kendall and I've been going through Dr. Barbara Ryden's textbook, Introduction to Cosmology. This is Chapter 3, Section 4, Describing Curvature. Today we're going to answer this question. What exactly is spacetime curvature and how can we describe it? Before I begin, I just want to say thank you to my Patreon supporters as well as my YouTube members. Their support means a lot to me because it does keep this channel going. If you like what's been happening on the channel so far, please join up. I also give all my supporters and members special perks and advanced views. So let's begin. What exactly is spacetime curvature? Last time we looked at how the Einstein Equivalence Principle shows that an accelerated reference frame can be the same as a uniform gravitational field. This means there is no experiment that can tell the difference between a uniform gravitational field and a uniformly accelerating reference frame, such as a rocket going up in space, whatever upward means in space. Also, when you drop a couple of apples here or there, their descent would be the same as if you dropped them on Earth. If you threw them to the right, their descent in both reference frames would make a parabolic curve. Now that's for the trajectory of falling objects. We also find that the equivalence principle dictates that light's path must also bend in a gravitational field. We found this by looking at the behavior of a laser in an accelerating rocket and applying the principle to show that it'd be the same on Earth. We're always assuming in these examples that the rocket's acceleration is the same as the Earth's, that is 9.8 meters per second squared. This is one of Einstein's great predictions, and it was borne out in the solar eclipse of 1919, where Eddington went and found the actual deflection of starlight as a result of the sun's gravitational field. Another test of relativity that shows this strangeness of gravity is the gravitational redshift. Inside of a uniform gravitational field, the light that is rising up and out of a gravitational field will lose energy as it traverses that distance. This was first quantified and tested in the Pound-Rebka-Snyder experiment. This experimentally demonstrated there is a loss of energy by photons going up inside a gravitational field. All these things kind of give us a hint that space and time are a little bit different than we expect them to be. In fact, they're significantly different than we expect them to be. So let's ask the question, what exactly is space? Because when we talk about space-time curvature, we naturally come up against a lot of preconceived notions, as well as that age-old bugaboo common sense and how it makes us want to think or not think about the nature of space and time. In this lecture, we'll focus exclusively on spatial curvature. I get a lot of questions in my videos' comments where people ask and plead and demand to know what space-time curvature is, and specifically, what's it curving into? It is very sticky for a lot of people to get the hang of the idea of what we mean by space-time curvature without it actually curving into anything. This is the key concept I'll try to explore today. Because general relativity and all of physics are mathematically based, and the language of physics and the language of cosmology and the language of astronomy and the language of science is mathematics, we must allow the logic of mathematics and its proofs and theorems to guide us in our search. The gold standard is when a theorem or proof gives us a method to test it in the real world. Theoretical physics is all about creating testable predictions based on other tests through mathematical analysis. We'll walk that walk and see where we end up. So let's start with the mathematical concept of space, which starts with just a bunch of points. That's the first concept of the idea of space, simple labels on points. Notice I did not say location in space. We'll first start by defining a space as a set of points. Next, how you relate those points together is really important. This is the topology on top of all these points. This topology will define the relationship or relationships between and among all the points. Perhaps it's just a map of this one, then that one, or these are alike and those aren't. Basically, we'll need to define how you get from one point to another as a way of thinking, or if there's any relationship between the points. and that's what we mean by space. It is not just some set of points, but it's also their interrelationship. And now we see our first bias and prejudice. We will likely ask, what's the distance between a couple of points? But that question is not a needed one for the relationship among the points in the space. They may be completely discrete and separate, so there may be no thing between some subset of the points or even all of them. Our points may just be labels for objects, and as mere labels, they don't contain a distance-like quality. At this point, you may be thinking, yeah, but that's not what we mean. I agree. It's now important to note that all of physics relies on a concept called a metric space. This means you have some rule that allows you to make a measurement of the distance between any 2 points in a space. And we're not going to say in space. I'm going to keep saying in a space. This important distinction arises because of our concept of space as a set of points. This is where common sense starts to fail, because the very way you measure a space is a matter of experiment itself, and not in the construction of rulers and levels and protractors, but in the way the tick marks of these instruments rely on a groundwork of assumptions about your world. Staying with the idea of a metric space, we can safely eliminate a huge swath of different kinds of spaces. A metric space is a space that allows you to make a distance between points. Now, we also have to have another set of concepts about space as well. We also wish to stick with some parts of our intuitive notion of space. Our intuitive notions about space contain the concepts of homogeneity and isotropy. Homogeneity means that pretty much if you look in large enough scales, everything is roughly the same no matter where you stand. It's much like the idea that all cities have a Starbucks on every corner serving the same coffee, or that every medium-sized town has strip malls and McDonald's. It is this concept of homogeneity I'm after. Now, there may be small differences when you look closely, like there may be some bookstores that sell comics in one town but not another. Or there may be 2 independent coffee shops in one town but none in another. But over large enough samples of towns, these differences smooth out. Or more specifically, looking at the county level, containing many towns, you start to see the same contents. No matter where you go, it's about the same stuff. A sad thought for some, but let's leave that alone. It's a core assumption in cosmology that the universe is filled with the same stuff, which behaves the same way on average no matter where you are. That's the concept of homogeneity. On the left-hand image, we see throughout that sphere pretty much any place you would go inside that sphere has some upward-directed arrow. Also, every location has roughly the same number of arrows in a given volume, and they're all pointing in the same direction. So that is quite homogeneous, but it's not isotropic because there's definitely a preferred direction of orientation. All the arrows point up. Isotropy means that it looks the same in every direction. Now, in the right-hand side image, it's distinctly isotropic, but not homogeneous. We can see there are different densities or different hashes. The stuff that's close to the center is clearly different than the stuff just beyond it, and then there's a sphere around that that's again different stuff. So it's isotropic around that one central point. And if we were there, looking around us, we'd see those 3 different layers all layered the same in every direction. But if we take a step to the edge of one of those spheres and look in every direction, now it's not isotropic. There would be different layers in different directions at different distances. That's the isotropic concept. But homogeneous, it certainly is not. Because if you take a bucket in any one of these areas, you're likely to get different stuff. So these concepts of homogeneity and isotropy are kind of the way we think about space in general, and this is experimentally verified. It doesn't matter what direction you look, it's roughly the same in all directions. And it doesn't matter where you are in the universe, you'll see roughly the same stuff around you and in equal parts. Both homogeneity and isotropy are part of what we call the cosmological principle. But it's also kind of intuitive in a way, and it helps us. Another thing that it helps us with is the nature of our coordinate systems. Now this is where we're starting to talk about what we really mean by the nature of space. Here's a metric space, meaning that each point in the space not only has a label x, y, z, or r, theta, phi, but also has some rule to measure the distance between the points. The labels make it clear that we're working in a 3-dimensional space. This means to fully and exclusively parameterize every point in space, we only need 3 numbers. These numbers can be assigned to places on a grid. Now, the grid of coordinates is not unique. There is an infinite number of possibilities, but we will stick to orthonormal coordinate systems, even though that is not strictly necessary. By contrast, a non-metric space would not necessarily even have enumerated locations on some grid. It just might have some index or some non-numeric naming convention for each point in the space. Luckily, we won't need to learn any more about such spaces. It is the application of some parameterized coordinate system to the space that solidifies the concept of a metric space. Let's declare that 1 step equals 1 meter. We can also declare that we can make a curve that smoothly traverses between two locations, and that each point on that curve can be associated with some real number, not just integers. Measuring the length of that curve, whether it's a straight line or some bendy, loopy path, is facilitated by the thing called the metric. The metric transforms points in a space, each labeled with coordinates, into a distance between the endpoints of the curve. Again, the curve between 2 points can be called a path, and this path curve in a metric space has a parameter that, as we go from point to point, will translate the continuous smooth set of points on the curve into a distance. Of course, the most common system for labeling points in space, is the Cartesian coordinate system, with orthogonal x, y, and z. We can also use a different kind of orthogonal coordinate system, the spherical coordinate system. Here we have a radial coordinate, which is some distance away from the arbitrary origin or 0 point. Next is theta, which is an angle from the z-axis down to the radial coordinate. Finally, we have the phi coordinate, which is just like a longitude rotating around the xy plane. Now notice that the center or 0 point or origin of the xyz system is arbitrary. That's a concept of a homogeneous space. We can set up our origin anywhere. As for isotropy, the exact direction of the z-axis is arbitrary. We'll call it up. But what exactly is up far away from a gravitational field? Thus, our orientation is also arbitrary, so therefore it's isotropic. It's easy to show that we can transform the Cartesian xyz into r theta phi. The dl of both these metrics is the distance between any 2 points in this metric space, and they are exactly the same distance. They only differ in their coordinate labels. Here we're only showing 1 point, but if we had 2 points, then their distance will be some distance change in x, some distance change in y, and some distance change in z, and that will give us the total distance change, which gives us a length between the 2 points. Importantly, a space doesn't care about what label it is. We use the most convenient label to solve whatever problem we have. Neither one is the one correct coordinate system. Also, the labels themselves, therefore, are arbitrary so long as they span the dimensionality of the space in question. The metric itself is also, in a very real way, independent of the coordinates. Its job is to translate coordinate differences into a distance. Let's now look at the difference between polar and spherical coordinates. Polar coordinates are just a different way to map points on a 2D surface. I won't use the word plane because that has a specific meaning as detailed by Mr. Euclid way back in the day. Spherical coordinates are in 3 dimensions and cover a 3 surface. That's an ugly way of trying not to use the word space. In both cases, the choice of origin is arbitrary, and though the coordinate setup looks different in each, the 2 different pairs of coordinates, the xy in polar and the xyz in spherical, in each case, the surface or volume is fully spanned and labeled by the 2 coordinates or 3, depending on the space's dimension. The 2D case does not necessarily need or rely on any aspect of a 3rd dimension, and by extension, the 3D case does not need or rely on a 4th spatial dimension. In addition to spherical coordinates, we could use cylindrical coordinates. Basically, they're just polar planar coordinates with the z-axis sticking orthogonally up from the plane. So we have this very simply connected space and spaces. And these coordinate labeling things are giving you an implicit bias about how you think about space. We think once you're out in space, there are no restrictions on your movements. And why not? I mean, there shouldn't be any unless you run into an asteroid or something, and unless you're writing some good sci-fi, you don't think of, say, going into space and all of a sudden hitting some wormhole or hitting some block in space or a boundary in space where you have to go around the boundary or you just can't go past a boundary in space. We don't think of space like that. we think of space as going on forever, just like Euclid said. And all these coordinate systems that we've been looking at support this common sense idea about space. Unfortunately for our common sense, there are an infinite number of spaces that are homogeneous and isotropic, and only exactly one of them abides by Euclid's axioms. To show what I mean, let's take this concept of a cylindrical coordinate system and play with it for a little bit. My goal now is to dislodge some of the biases you may have concerning the, quote, obvious nature of space. I'm going to help you first with the old 1979 video game Atari Asteroids. When you play Asteroids, you're piloting this little spaceship around trying to blow up some asteroids, and as you do so, the asteroids float through the space of the video game. Now, if a rock or an asteroid goes off the right-hand side of the screen, here denoted by the green boundary, then it'll appear immediately on the left-hand side on the other green boundary. Therefore, the right-hand side and the left-hand side are stitched together, kind of like a cylinder. It's very similar to the coordinate system we just looked at, except now you can't go into or out of the screen. You are in a two-dimensional space that feels like it has three dimensions. A good way to describe it is by imagining that the left and right sides are stitched together into a cylinder that has some fixed radius. And this radius is easy to describe. Take the width of the screen and divide it by 2 pi. That's the radius of this cylinder. Now, this is still a completely 2D space. It's just not a simple space. The relationship between the points in the space is different than the simple Euclidean plane. However, a cylindrical surface can still abide by Euclid's axioms. We next throw Euclid completely out in the asteroids game because the cylindrical space is also reflected on the top and bottom. It's a double cylinder. The top is stitched to the bottom in exactly the same way the right and left-hand sides are stitched together. So you can go up, cross the top, and then appear at the bottom. Now that's very hard to visualize. In addition, it's not a sphere. A sphere would also stitch the right-hand side and left-hand sides together, but the top line would now need to become a point. Also, spheres don't connect the North Pole to the South Pole. This means the space of asteroids is a torus, or donut shape. To see why it's a torus, imagine a circle drawn on the screen. As long as the circle doesn't cross the stitches, then you can shrink the circle to a point. But if the circle is big enough to cross the stitches, then the best you can do is to make it a straight line. But notice we can still describe the entire space of asteroids in 2 dimensions. We just have 2 special rules that we add to it. Go off the right, come from the left, go off the top, come up from the bottom. But the location of those stitches is arbitrary. It's just the boundaries of the video screen, and that's all it is. The visualization of the torus that you see exists only to help you understand it. Philosophically and mathematically, there is no physical reason for the 3D world to exist in which the torus appears. We only need the 2 dimensions on the surface of the torus to make the Atari game space work. We can further demonstrate the potential weirdnesses of spaces with some etchings by M.C. Escher. His Ascending and Descending from 1960 displays 2 lines of monks, one continually ascending and the other continually descending on the same set of stairs. The stairwell is drawn to be a perpetual loop. An interesting concept because this is a 2-dimensional surface, right? A piece of paper. And on it, we have a 3-dimensional sort of building, which obviously cannot live in a normal 3-dimensional world. No matter how you would look at this building, it can't be built in reality. One of his classics is Relativity from 1953. This one is even more mixed up than the Stairs of Monks. You can't imagine or determine which way is down because there are so many downs in this image. You can continuously traverse this stairway around and around and around, or down and down and down. And each time you do, you have to rotate your orientation based upon the current notion of down. So this is a non-simply connected 3-dimensional sort of space that is projected onto 2 dimensions. But to its embedded dimensionality, there could be perhaps a 4th spatial dimension. But I'm not sure. No matter what, this can't exist inside of any 3-dimensional real universe. Importantly, though, how would you assign coordinates to this space? No matter how you do it, you will necessarily need to have cross products in the metric. That would mean that the distances would rely not just on the squares of x, y, and z, but on the products xy, yz, and xz. What a yucky setup. I leave its devising to an extremely intrepid student. The real reason to talk about all this is to loosen up the concept of space and dimensionality. We can clearly create, quote, impossible objects so long as the objects obey certain rules. Then they no longer appear impossible. We can create rules of spaces that allow for non-simple connectivity and non-trivial spaces where lower dimensional spaces can be sufficient in of themselves without demanding additional, hidden, or imperceptible dimensions. This is the beginning of the intuition to understand why space can be called curved, yet it doesn't bend into anything or out of anything. We won't deal with spaces like Escher envisioned. We will look at spaces that evidence seems to point to that fit our reality. Remember that a space is simply a collection of points. We can relate sets of these points to other subsets of these points in any way we choose. But it's a matter of experiment as to whether or not these connections we chose fit reality. Our intuition may not be the correct guide. For example, we know from previous lectures that the path of light is curved in a gravitational field. Now let's see what we get when we look at the universe's global curvature. We have to start by going a very long time ago, 300 BC, to visit Euclid. He wrote the great masterwork on geometry called The Elements, which is very much worthy of study today. Every high school student doing geometry studies Euclid's axioms. These 5 axioms of Euclid are fundamental and give us the basis of what we would call flat space or uncurved space. This starting point harkens to our most intuitive way of thinking about space. The first axiom states that you can draw a straight line segment joining 2 points. It may seem obvious, but that's the purpose of axioms, to explicitly declare our intentions. What an interesting concept, because you can take any 2 points, no matter where they are in space, in a Euclidean flat space. Now let me start using that word, a Euclidean flat metric space. We can now draw what we might call a straight line between them. We don't have to curve around anything to join these 2 points. The fact that Euclid uses the word can here is also interesting. It implicitly means that along that segment, we can stop anywhere and choose any of the infinite number of points on that segment to make a shorter segment. The second axiom extends the first to state that carrying the line's direction along the same direction it was a tiny step ago, we can make arbitrarily long segments, each dense with points. This is a key concept of the real number line and a key idea of what we think of as space. We can always find space between any 2 points. Furthermore, the space between them has no kinks, whereby we have to change direction in order to go from one point to an arbitrarily close point. This changes and extends the idea of a line segment into a line. In relativity, we would call this concept a geodesic. Euclid's second axiom posits an infinite universe. He means that every line segment points off to infinity in either direction of the segment. You just have to take the time to walk it, which of course you can. Again, I want to point out that you could lie an arrow down on the segment and push it along so that the arrow is never askew from the segment. The arrow will then stay pointing in the same direction as you push it off to infinity. The third axiom now relates line segments to areas and specifically gives a method to create the model of perfection, the circle. The third axiom could have used a square to give the concept of area, but the circle was a deep puzzle to the ancient Greeks. They understood that even though it could be created with a fixed length segment, there is no integer or fractional value of the segment that can be laid perfectly around the circumference. That's the whole 2 pi r thing. It was quite a mystical concept, but this was just a small part of why circles became regarded as symbolic of the celestial or heavenly realm. Euclid was giving us a way to relate the mundane to the sublime. The fourth axiom is also very odd on the surface. Axioms are weird because they always state the obvious. So, right angles are congruent. This simply means that every right angle is the same as every other right angle. That's an interesting statement of the homogeneity and isotropy of Euclidean space. Euclid here expands his geometry into the third spatial dimension by taking the highly obvious exercise of taking a t-square and rotating it around in your hand in any possible orientation. If you take a t-square and rotate it, Euclid's axiom states that it does not change. It also states that any reader of his elements can do this at any location. and implicitly at any time. Only the second axiom asks us to try to do some action by extending a line segment. This second axiom states that if you were to do this, then there is no end to the line or its straightness. The fourth axiom allows us to toss right angles around however we want at any time in the past or future, and they will always stay the same. We can also note that a right angle is composed of two line segments. This axiom also means that we can extend the segments indefinitely, and that angle stays a right angle. We can take a segment out of the infinitely long lines radiating away from this right angle vertex and drag it, arrow style, all the way back to the right angle vertex, and it'll still be lined up with the original line segment of the right angle. This is a really important concept to grasp as we go forward into curved spacetime. Euclid's line segments, once laid down and extended, keep their orientation and their straightness in the common sense way of thinking, and in the carried arrow way of thinking. Spacetime curvature will have something to say about this. Now then, the fifth postulate is the one that we're going to play around with a lot. Let's start with two lines. These are our infinitely extended lines. They could be in any orientation in 3 dimensions, but we want them to be in the same plane. So now we have these two lines. Now we toss a third line into the mix such that it intersects both of our original lines. If we examine the interior angles of both sides of the intersection, we will then choose the side where the sum of the two angles is less than the sum of two right angles, that is 180 degrees or pi radians. Let's then follow our original two lines on that side all the way out to infinity. Euclid's axiom says that well before we reach the lazy 8, those two lines must intersect. Now this is an interesting thought. It's distinctly not like a pair of train tracks. Train tracks, even though they do seem to converge in the distance, we know they never do. The railroad ties keep the tracks at a fixed width for the length of the train track. This means that at every point along the train track, the ties intersect at 90 degrees or at right angles to the tracks. The train tracks are parallel, but generally, two lines extending off into the distance are not. For any two lines on a plane, there's exactly one orientation of both lines such that they are parallel. All other orientations mean that they will eventually intersect. This is the concept of Euclid's fifth postulate, known as the parallel postulate. But here's the thing about the parallel postulate. It was found in the 19th century to be unprovable from the other four postulates. It was also shown back then that we can devise mathematical spaces where the fifth postulate does not hold. That is, where infinitely long straight lines in the loose sense pointed towards each other away down the road will never intersect, even if they're on the same plane. Likewise, we can devise spaces where such non-parallel lines intersect an infinite number of times. Worse, we can make spaces where in one place, say where you started, they're parallel in the Euclidean axiom 5 sense, but far down the road they intersect, or diverge. There are an infinite number of spaces where the carried arrow idea gets messed around with, and the arrows get turned around, even though they were locally stepped along in the normal sense of the word straight. Let's start by taking a closer look at Euclid's second axiom. Any straight line segment can be extended indefinitely in a straight line. The sense is that we have some direction to that line and we want to take little steps in that same direction. So we can have an arrow that leads us down the line. This arrow is being moved with a process that we'll call parallel transport. Parallel transport really means moving a vector along a geodesic tangent to the space such that it remains pointing in the same direction as you move it in tiny incremental steps. For a flat space, this is a nearly trivial and obvious exercise. We can also parallel transport an arrow along a different geodesic that intersects the original geodesic. In both cases, we always mean to say that a geodesic is a straight line in that space. Again, in a flat space, this always means the trivially considered straight line. Notice in the second case that the arrow was parallel transported along the second segment but maintained its orientation. That's the essence of parallel transport. We can then define the curvature of a space to be the amount of deviation, if any, that a parallel transported arrow endures as it is transported around a closed loop. In a flat space, the arrow will always stay pointed in the same direction, never leaving its orientation. This is exactly the same as pushing the arrow around on a table and always keeping it pointed in the same direction. But in a curved space, the orientation of the arrow will change upon traversing a closed loop. The direction and amount of rotation determines the shape of the curved space at that point in the space. Here we still haven't limited spaces to anything. A space could be flat here, radically curved there, and only mildly curved somewhere else. But a curved space will always change the orientation of an arrow as it is parallel transported around a loop. So let's take a good first example of such a space. The surface of a sphere is a two-dimensional space. At every point on the sphere, there are an infinite number of tangent arrows that are in the space. Let's choose one such arrow and take it to be pointing towards smaller longitude. Now let's step that arrow along a geodesic, here the equator of the sphere, always keeping the orientation of the arrow as close to parallel as you can as you step it. Now you might be saying, a sphere has a curved surface, so if you move the arrow at all, it'll have to rotate. And that's exactly true. So we have to move the arrow in such small steps that we cannot sense this change. However, even if we do this, the changes will add up. We turn the arrow now to go longitude line up to the North Pole. This is a bit easier to get since the curvature isn't in the direction of the arrow. Once we get to the North Pole, we descend back down the longitude line leading to our original starting place. When we arrive back home, the arrow has been rotated. Each step of the way, we took pains to assure that the arrow was always carried parallel transport style along the geodesic in a straight line on the surface of the sphere and remaining pointing in the same direction. Obviously, the surface of a sphere is curved. It's always interesting to do parallel transport for the flight path of a plane. Taking this very long flight from LAX to Heathrow is done on the geodesic, Great Circle line in red, and certainly not the black line. However, just for fun, take a black arrow and point it in the Mercator projection from LAX to Heathrow. The angle between the Mercator straight line and the true Great Circle straight line is 49 degrees. Notice how the black arrow, when transported between 2 points on a straight line in the two-dimensional spherically curved space, will rotate quite a bit. The black arrow is basically the viewpoint of someone looking out a window, and the pink arrow is the true direction of the plane. If we were to have instead forced the transport to occur along the blue line, which appears straight, but is actually the curved line, the same rotation would occur. And this is because instead of one big path as we see here, there would be ever tinier small hops from point to point. Each smaller hop would be closer and closer to a Euclidean straight line. However, because the Earth's surface is curved, these little hops along the truly shortest distances will still add up to the same total rotation as before. Let's now examine the three uniform, isotropic, and homogeneous spaces. All three have globally uniform curvature. This means that every point in the space experiences the same exact curvature. There is no mix of flat and positive and negative curvatures in each of these. Again, the curvature is always best noted by its impact on navigating the perimeter of an area. To help show the effect of curvature, I'm going to see the effect of an arrow that's tangent to the circumference of the circle in the space. This is different than parallel transport. In a zero curvature space, the circumference of a circle is equal to 2 pi times the radius of the circle. In this case, this also means that the tracing of an arrow tangent to the circle works out to be the same as parallel transporting the arrow around the circle. A flat space circle has circumference of the expected 2 pi d, where d is now the radius, and now 2 pi is the total angular rotation of our tangent arrow that it will incur as it traverses the circle. As we saw in the positively curved space, the arrow will lose some of its rotation as it's transported around a closed path. The lost angular shift is due to the circle's circumference being shorter than that of a circle with the same radius in a flat space. We saw previously in a counterclockwise traversal that the arrow's rotation loses some angle in a counterclockwise sense. From this diagram, it's like a chunk of the space is missing compared to flat space. If we follow the red arrow around the circle starting from the bottom, we see that it doesn't fully rotate compared to the flat space circle. However, it still did execute a circular path in the two-dimensional positively curved space. The area of such a circle is larger than a flat space circle, but its circumference is smaller. This should be familiar to you when you look at global maps of the Earth. Any projection distorts the sizes of the continents. A sphere must be spread out in order to be projected onto a flat surface. To retain the sphere's spatial proportions on a flat surface, you have to slice it into ribbons as we see here. The diagram shows us traversing a circle that's a latitude line, which is not a great circle. This means that when you parallel transport it, the arrow has to change orientation as it hops from one great circle to the next in tiny, tiny steps. In my red arrow example, it has not been fully rotated by 360 degrees or 2 pi radians. It's short some tens of degrees. In the negatively curved space, this transport of a tangent arrow around a circle would result in completing the entire rotation and then some. This is because the circle circumference, in this case, is greater than the flat space case. The parallel transport would pick up that greater length as the arrow hops from one tangent in the space to another. Rather than great circles in a negative space, we could call them great hyperbole of the space. In short, it's encountering a greater angular change as it's carried along the circle. These circles' areas are smaller than flat space circles, but their circumferences are much, much larger. Again, curvature is defined to be the change in rotation of a tangent arrow in the space as it traverses a closed loop. Let's look at each of these spaces in turn in greater detail. Let's start by looking at two-dimensional spaces. And we'll also exclusively look at homogeneous and isotropic spaces. That's very important. Having two dimensions in a space means that there are two and only two free parameters for assigning locations to events in the space. Two-dimensional spaces can be called surfaces if they're embedded in a three-dimensional space. We'll learn more about embedding shortly and why it matters or it doesn't matter. In Euclid's flat 2D space, we can use the simple metric that we see. It is sum total dl squared, which equals dx squared plus dy squared. In more detail, we've got an x-coordinate, which is left and right, and y, which is back and forth. A little change in x is called dx, and a little change in y is called dy. You square and add them to obtain the square of the distance between 2 points, x1, y1, and x2, y2. This extremely simple relationship transforms the coordinate changes between two locations into a distance. The metric can also be expressed in polar coordinates rather than Cartesian coordinates. We declare x to be r cosine theta and y to be r sine theta. The r is some radial distance from some declared origin point. Theta is the angle from the x-axis towards the y-axis that this radial distance points. These two metrics, though they look different, will give the same answer to the question of how far apart any 2 points are on a flat 2D surface. And this is our first metric. It is, admittedly, a very basic metric on a flat two-dimensional Euclidean surface. But don't worry, things will get more complicated. Notice right off the bat that this metric in both coordinate forms is inherently isotropic and homogeneous. The origin point is arbitrary, and there's nothing in the metric that says anything special about the locations or orientations. There is no cross product of dx and dy, and there are no rules say that if you go over here, you'll appear over there, like in asteroids. A key idea about a flat space involves the interior angles of polygons, and so let's start with a triangle. If you look at the interior angles of triangles, let's call them alpha, beta, and gamma. If we add up the total number of degrees of the three angles inside that triangle, we get 180 degrees, or pi radians. It wouldn't matter which of the metrics you use to derive this angle, you'd get the same result. Everything that Euclid would be comfortable with is on this slide. And let's see where that comfort breaks down. Now let's look at the surface of a sphere. A spherical surface is still a two-dimensional surface, and it is distinctly not flat. It is certainly curved. We can call that curvature positive. Why? Because the sum of the interior angles of a triangle and the surface of a sphere is always greater than 180 degrees, or pi radians. The angular size difference is the area of the triangle divided by the square of the surface's radius. So now I need to start to talk about embedding. Embedding is for visualization purposes only and does not reflect another degree of freedom. The radius of curvature is not an extra dimension in space. Rather, it is a characteristic of the space. We can get the sense of the embedding here by noting that the little r is the distance on the surface of the sphere from the North Pole down to some point. That means there's a maximum distance between any 2 points, pi big R. This is one time where the choice of coordinates is a big help. Note that in the Cartesian coordinates, we would have to have x, y, and z, but with the restriction that the sum of the squares of these 3 coordinates is some fixed number r squared. The addition of this restriction on the Cartesian coordinates reduces it from a 3D space down to a 2D space. This metric with this restriction is certainly valid, but it's clunky and it's messy to use. You sure could eliminate the z-coordinate, but it's pretty repulsive. It's better to simply use a better coordinate system that fits the space. This is the plane polar coordinate system adapted to the surface of a sphere. Little r is the distance down from the North Pole, and phi is the longitudinal angle. The large type metric looks very different than our flat Euclidean space. Note that there are only 2 degrees of freedom, little r and phi. The big R is the characteristic of the space of the metric and does not represent an actual positional option in a 2-dimensional space. This all means that the spherical nature of the space, as we visualize it as a ball in the air, is not how the space is parameterized. The location of this ball in the embedding space is irrelevant to the discovery of the distances on the ball's surface. The actual size of the ball isn't really important either, except to create a scale factor if we want to measure in meters or miles or light years. No matter the size of the ball, we can devise 2 coordinates that are independent of the size of the ball to measure the coordinate distances on the ball. These coordinate distances will then be imbued with a physical distance when we determine the size scale of the ball using big R. In that sense, we can call this 2D space a spherical surface because this space shares many similarities to the thing that we call a ball. But as we can see from the metric, we are only ever making changes to little r and phi to determine a distance. Therefore, the embedding of a ball in the air is all just a mathematical trick to help you understand the space better. It does not imply anything about the space in which it is embedded. It doesn't even imply that such an embedding space even exists. The game Asteroids had a rule: go off to the right, come back on the left. That comprised the very nature of the space of the game. The developers did not need to solve any distances on toruses to find the curvature or the size of the space, nor did the game have to be viewed in the round. Nope, it was a flat screen with an odd rule. Here, we can look at the metric as just a mathematical tool for knowing the distance. The big R is just a scale factor, and the sine squared term is merely the only way to have a positively curved space that is homogeneous and isotropic. Many other functions could have gone there, tangent for instance, but only the sine function with that specific argument and that specific coefficient satisfies homogeneity and isotropy. Nicely, Euclid's parallel postulate fails for this space. All distance lines make great circles in this space, and therefore any lines that locally are parallel at some point will converge in both directions. Now let's derive the 2D metric that is congruent to being on the surface of a sphere. We start with a homogeneous and isotropic flat 3D Cartesian coordinate metric to define our embedding space. Next, I list out the x, y, and z coordinates in terms of their 3D spherical coordinates. I use r tick as the radius from the arbitrary origin in the 3D embedding space. Again, I want to emphasize that the 3D embedding space is a mathematical construct that should not be construed to actually exist. We know that the space we wish to bring into existence is only and exclusively 2-dimensional. We're just using the concept of an embedded space to help us derive a 2D homogeneous and isotropic space as a subset of that space, which retains the properties. Let's get back to the coordinates. R tick is the radial distance from some arbitrary origin to any point in the 3 space. Theta is the angle at which the radial distance vector lies from the z-axis down towards the xy plane, maybe read it the equatorial plane. Finally, phi is like longitude. We'll at least keep that around for later. Our major restriction is on the fixed radius, which then allows us to make, say, the z-coordinate into a dependent variable. X and y remain independent. We now define a new r. This r is the length on the surface of the sphere from the North Pole down to the point in question. Theta was going to be an independent variable in the spherical coordinates, but now it's subservient to our new r. The greatest possible length of our new r is pi big R. Why not 2 pi r? Well, then we'd be going all the way up the other side, which could then be described with theta r, with that theta measured from the opposite direction. So big pi r is the largest length in this 2D space. With this restriction of our new definition of r, we have a new series of x, y, and z coordinates. These new values only depend on r, on little r, and phi. We can then take the differential and then square them. Adding up these squares gives the form of the metric we saw before. It's worth emphasizing that this new little r here is distinctly different from the little r of the normal 3D spherical coordinate system. It reflects the fact that we must measure the radial polar coordinate component of this 2D system in the system and not outside it or through it. We only measure distances inside the 2D surface. And when I say inside the surface, I do not mean the interior of the sphere. I mean we're only measuring the latitude and longitude positions on this sphere calibrated with the big R scale factor to know the distance. I use in because we do not care about the 3D embedding bulk that may or may not exist. Mathematically, we could have derived this without resorting to familiar geometrical ideas. It is a lot harder to do and would require some mathematics quite beyond the scope of this lecture, but it can be done. It is this embedding that trips people up and is the source of all preconceived notions that a curved space curves into some other space. The curved into space was a complete construct and helper function that merely gave us a shorter path to the same answer. Another way to look at it as the embedding idea is a model and not reality. The model is a good way to think about it, but like all models, it has its limits. If I'd never shown you the words spherical curvature and merely showed you the metric, you wouldn't have necessarily started with the concept of a 2D space embedded in a 3D space. You'd have just said, well, that's an interesting way to connect all the points in a 2D space, and left it at that. Unfortunately, for students of spacetime around the world, this bias lives on. The only way the 3D would come back is if some physical process happened to be on this 2D surface that demanded a third spatial dimension for its action. We are only and exclusively looking at length measurements, so the third dimension was there just as a helper tool and not a degree of freedom. For our third and final homogeneous anisotropic space, we have a uniform hyperbolic negatively curved space. In every location in this space, the space kind of folds away from itself. The parallel postulate here says that initially, parallel lines in this space all diverge, growing in distance apart. Concerning the sum of interior angles of a triangle, it's now less than 180 degrees or pi radians, where the difference is the area of the triangle divided by the square of the characteristic curvature. But what's this radius around? That's a good point, because when we look at a negatively curved space, we really cannot visualize it very easily. We see these saddle-type shapes as examples in books, but it's really deceptive. Why? Because every point in the space would be centered on a saddle-type shape, and all space around every point folds away from itself. And this is an infinite space, but its shape is radically different than the Euclidean infinite flat space. In some sense, the farther away you go, there's more space there. This can be seen in the odd metrics form. Compared to a positively curved space, the sine function is replaced with a sinc function, which is basically an exponential for large values of its argument. Unlike the uniform positive curvature, which has a maximum value of little r over big R, there is no maximum value for the hyperbolic sine function. Its role here is to make initially parallel lines diverge away from each other exponentially. The saddle shape is just a helpful visualization that the space is exponentially more dense than the flat plane. However, it's still only a two-dimensional space. We have to embed this in 4 spatial dimensions in order to get a 2-dimensional spatial metric. Those extra dimensions were, again, bound by restrictions that made them dependent variables to the two real dimensions. They then simply get tied up into the characteristic scale of this space, big R. This big R, again, is more like a fundamental constant of space and not a spatial degree of freedom. All right, so now I've summarized the three equations that you've just seen, and I've extended them into 3 dimensions. The symmetry of the angular rotation allows us to extend the metric from just theta and into phi as well. Theta was a longitudinal rotation, and phi now is an equivalently latitudinal rotational degree of freedom. It's the same set of coordinates we saw a bit ago when we examined the coordinate embedding of a spherical positively curved space in 3D. But without the radial restriction, we now work in all 3 dimensions. As we can see, we can simplify the equations by defining omega. In doing so, we can combine these equations into s sub k of little r to give us a happy shorthand notation. This function has 3 values depending on the value of k for the curvature, which can either be +1, 0, or -1, each one representing the curvature of the space. What's more interesting is that s of k of r can be represented analytically with that wild-looking function on the bottom right. These coordinates are called hyperspherical coordinates because they describe an embedding of a 3-dimensional space in a 4-dimensional space, as we derived previously. These equations represent what we might call a 3-surface of a 4-ball. That is to say, the 3-dimensional surface to a 4-dimensional hypersphere. Wild circumlocutions aside, the embedding is still just a mathematical trick or tool and not a reflection of a physically needed degree of freedom. With that, let's see what the form looks like when we embed a 3-surface into a 4-ball. Let's start with a space that has 4 spatial dimensions. We have our familiar x, y, and z, and now we'll toss in a mystical w. The Cartesian spatial length element is given at the top. A small change in distance, dl, is the sum of the squares of the little changes in each coordinate distance. Next, we'll add the needed restriction that we're looking at a 3-surface. Normally, we'd call that a sphere, but a solid sphere in 4 dimensions requires 4 coordinates. Thus, we're looking at what we would call a hypersurface. This restriction works out to be the sum of x, y, and z squared equal to a radial coordinate, little r. That's just the definition of our hyperradius. Our restriction comes into full force with the second part. W squared plus r squared equals big R squared. Now we've bounded the hypersurface with the big R. Big R here is the radius of the 4-ball that is wrapped by our 3-dimensional hypersurface. I've taken the liberty of converting x, y, and z into polar coordinates for the next line, and this should look quite familiar. It's the same thing we just looked at in the previous slide for s sub k of r for k equals 0. Basically, this statement means that we're embedding a curved 3 space in a flat 4 space. However, our embedding dimension is just a tool and not real. If we take the differential of our restriction condition and square it, we get dw squared equals dr squared times r over w squared. This leaves us with dw be converted into little r, scaled by the restriction constant big R. Plugging this dr back into the 4D spatial metric and sampling with a tiny bit of algebra gives us a new form of the metric. We can then define k to be the inverse of big R squared. Here, k is the curvature constant and can range from plus big values to 0 to minus big values. Previously, in the hyperspherical coordinates, it was either +1 or 0 or -1. This k is different. The final form of this metric for positive values of k is given on the right, where we've once again used the isotropy of space to emphasize the simple angular dependence. Not all 3D spaces can be embedded by placing them in just one more extra dimension. A 3-spatial dimension negatively curved space with k less than 0 requires 2 extra spatial dimensions for the embedding. I could follow the argument through here, but suffice it to say that the mathematics are tricky and the bang wouldn't be worth the buck for this video. As you can see, this simple restriction would lead us down into the complex plane, requiring a bunch of proofs about complex analysis and much more. The end result is quite similar, though, to the previous slide, except now that the values of k would be negative real numbers, and for your edification I've chosen to show the spatial metric for k equals -1. The saddle diagram here is a real failure for visualization. The cartoon only shows a poorly approximated 2D surface that is represented at exactly one point near the center of the saddle. Every other point in the space would also be represented with such a saddle shape around it, and such diagrams would get messy really fast. And that's just 2D surfaces. Now we're talking about a three-dimensional saddle. That would require being able to see it unfolding into that extra dimension on paper or screen, which is only 2D. The fifth spatial dimension is now required in order to accommodate the unfolding of the 3D hypersurface into an unfolding 4D negative space. It is this second step into a flat, five-dimensional manifold that finally gets us to our rotational symmetry. This is some ugly arcana. Perhaps one day I'll do a full video detailing this proof, but since it's not relevant to our current level of discussing cosmology, that is, we don't live in a space with 5 spatial dimensions, much less 4, I'll just stick with stating quite unsatisfactorily that it's serious maths that get us to this very simple metric we see at the bottom. The important thing here, though, is that we have a completely different form for the metric. The bottom metric is indicative of a globally uniform, isotropic, and homogeneous constant negative curvature three-dimensional space in some new coordinate system. Let's finally give a name to this new coordinate system. It's called the Reduced Circumference Polar Coordinate System. In this coordinate system, the little r is completely different. Importantly, the form of the metric in this coordinate system looks very different too. Here we have the curvature not being one of the three values, but rather some global constant with a real number value. The theta and the phi are the same as before. So what is this new r? Here is our metric expressed in two different coordinate systems. The top one is the hyperspherical coordinates, and the bottom one is the reduced circumference polar coordinates. The omega is the same in both cases. This is because of the inherent isotropy of these constant curvature spaces. In the hyperspherical coordinate system, little r is what you would normally think of as a radial coordinate. It's the distance from the origin to the point in question. In the reduced circumference polar coordinates, the little r is the length corresponding to the circumference of a circle centered on the origin divided by 2 pi. These two definitions of little r are not the same. They can't be used interchangeably, but the dl squared that they give rise to is exactly the same. There are very likely a whole lot of you are thinking one of the two questions at this point. 1, but isn't the circumference of a circle always 2 pi times the radius, so aren't these the same? And 2, why bother with making these two metrics at all? If you're going to get the same answer, why mess with these different ones? Can't you just tell me which metric is the right one? The first question is easy. We saw that in curved spaces, circles are either bigger or smaller than their flat space counterparts. The second question I can best answer by asking, what problem are you trying to solve? The first form will be helpful when we want to understand the angular sizes of distant galaxies, as well as keeping the form simple for the concept of distances. The second form is much more suited for calculating orbits. Each coordinate system has its benefits and drawbacks. In the textbook, Ryden uses the hyperspherical coordinates because we are frequently concerned with how the universe looks in all directions around us. We'll want to use this metric to show us how light rays traverse the cosmos from there to here. We show our cosmic bias because we're always at the center of all our observations. If somehow we could bop around the cosmos and construct a truly epically gargantuan circle or triangle out of lasers or cotton string, then yes, we would directly measure the curvature of the universe with the second metric. Irrelevant to its practicality, this would be an excellent way to measure the universe's curvature. But alas, we are tiny critters who will never make it to the next star in the next 100 years, much less into intergalactic space. We've been talking a lot about metrics and how they measure distances between 2 points separated by small intervals. I want to show you what a metric really looks like and how we get curvature from it. To finish out this long video, we have to lightly skate over some heavy maths. So buckle up, here we go. The metric encapsulates all aspects of the space into a compact form. It determines at every point P in the space the way we measure the distance at that point for each coordinate direction in the space. Thus, we have a bunch of coordinates, and they can be in any coordinate system that spans the space. The space has n dimensions, and we have some dxi or dxj for each one. The superscripts and subscripts I and j are just indices that help us keep track of the coordinates. With 3 spatial coordinates, we would like to use n equals 3, like we've been doing for this entire set of slides. The double summation sums over all possible combinations of the coordinates. I ranges from 1 to 3, and so j also ranges for our previous examples. We've just had the good fortune of choosing and working with metrics with a high degree of symmetry. This makes the components of the metric really simple. Here, in this particular metric, there are only 3 components. We could have had 9, owing to the double summation over I and j from 1 to 3 each, but we don't have any cross products of phi, theta, or little r. We only have their squares. As you can see, 6 of the 9 possible metric components are exactly 0. On the right-hand side of the summation, I've also reduced the form down to a simpler-looking thing. I haven't changed anything significant, I've just used the Einstein summation convention. When doing such tensor algebra, if you have a subscript I that matches with a superscript I, then you sum over all possible values of I. Little g is the thing we call the metric. Let's say that when I equals 1, that coordinate is now assigned to little r, and when I equals 2, that's theta, and I equals 3, that's phi. This metric only has non-zero values for g11, g22, and g33, which correspond to grr, g theta theta, and g phi phi. Notice the values of g for each of its components vary from point to point, specifically for differing values of little r and theta. The coordinate value of phi doesn't determine the metric's values for any point in the space. This dl squared is just one example of a metric. We can imagine whole bunches of different metrics. Some may even have physical significance. You can write the metrics however you want, with any symmetries you wish, or with none at all. It's just important to note that the metrics encode all aspects of the space and relate tiny changes in the coordinates to physical length measurements. Let's see what we can do with a general form of g, the metric, and we have to remember that the Einstein summation convention is in effect. It makes our equations look a lot nicer, but we'll have to keep track of this one abstraction as we read along. In a previous lecture on the equivalence principle, I showed how light's path is bent in a gravitational field. I also showed that this path is called a geodesic. A geodesic is just following the shortest path in the space between 2 points. The metric for any space is given in the upper right. ds squared is now a space-time interval, and we're not restricting it to just spatial dimensions anymore. The gij is summed over the products of the various coordinates, which we're now allowing to have cross products. We can then define a thing called a Christoffel symbol, which is the capital gamma on the upper left. It has 3 indices, 1 upper and 2 lower. Each are different on the left, so no summing yet. But on the right, we see that it's the sum of the first derivatives of the metric, all times the metric itself on the left. Now, we have a mix of upper and lower indices, but importantly, the index L is the summed index. See how it's on top outside the parentheses, but on the bottom for the items inside the parentheses? That means we're summing things up according to the Einstein convention. So, while this is a shorthand for L ranging from, say, 0 to 3, we would have had 4 of these added together, 1 for each value of L. The summation convention keeps things compact and easier to read. But why does this thing exist, this gamma, this Christoffel symbol? What's its use? On the bottom is the geodesic equation. This equation shows how each coordinate, dxm, changes as you step a little distance, ds. The Christoffel symbol tells us the gradient of the space at a given point for each coordinate. As you traverse some small path length element, going on the shortest path, the gradient describes the path's curvature. Again, the metric contains all the facts about the space at each point, and the Christoffel symbol relates those facts to the shortest trajectory in that space, called the geodesic. The red line in the box is due to a gravitational field. That path is determined by the geodesic equation. The metric for that space is called the Schwarzschild metric and is applicable to stars and planets and black holes, but not to cosmology. But that path is curved. So how do we then parameterize the curvature of the space, given that we can now determine the shortest paths in the space? Before we proceed, we need to see what these Christoffel symbols look like. Let's just go back to our original spatial metric with 3 dimensions. We have our original metric components in the red upper left-hand corner box. The components of the metric are only GRR, G theta theta, and G phi phi, each with the values that you see. To compute the Christoffel symbols, we also need to determine the upper index versions of the metric. I've put them all in the purple box. Each of these is the inverse of the double lower index counterpart. We simply want the product of the double upper with its corresponding double lower to be exactly 1. On the bottom are the things we need to calculate in order to get all the various Christoffel symbols. These are all the first derivatives of the metric with respect to each of the coordinates. Since there are 3 components to the metric and 3 coordinates, we need 9 first derivatives. I'm using the really compact comma notation for partial derivatives with respect to each coordinate rather than the more traditional dg dx style that you see in the Christoffel symbol. This makes it even more compact and for the ease of writing on blackboards and keynote slides. After doing the algebra, we end up with only 4 non-zero derivatives. Let's see how to use them. With these first derivatives of the metric in hand, I can now evaluate each Christoffel symbol, shown in green in the upper right. There are a whole wad of these because M, I, and J all have to take the various combinations of R, theta, and phi. Luckily, a bunch of them are 0. I'm only showing you the non-zero Christoffel symbols. The yellow ones all have the upper index as R. Here I've evaluated the upper index M for coordinate R. We get 3 non-zero symbols for R. Interestingly, each of them is dependent on the curvature constant K. For a flat space, K would be 0, which would simplify these symbols a bit, but K can be a positive or negative number that is constant of the space. It is in these symbols where the curvature shows up. The other symbols, which are principally angular dependency values, do not rely on the curvature constant. Also, none of the symbols depend on the coordinate value phi. These 2 factoids demonstrate the isotropy of the space. What they're saying is that if the gradient of the space as we orbit or curl around the origin at some fixed radius r changes due to the curvature, then the curvature in one direction would be different than the curvature in another direction. We already know that this is not the case, so these symbols just encode the isotropy in these mathematical artifacts. All these symbols can now be used to calculate the intrinsic curvature of the space. Let's see how to do that. The answer is here, the Riemann curvature tensor. A little while back I described the process of how we can determine curvature by parallel transporting an arrow around a short loop following geodesics. If the space is curved, then the arrow's final orientation and possibly its magnitude will deviate. Now we can finally quantify that statement. The Riemann curvature tensor is the thing you get when you actually do this experiment in curved space and make this measurement. This tensor, which you can think of as a powerful function, takes as inputs the coordinate basis for the space, some vector you want to push around the space, and the lengths of the sides of the loop. In this diagram, the starting vector is yellow v with an arrow over it. That's the red arrow pointing straight to the right above it. We then parallel transport yellow v upwards a distance dA. It might have changed a little bit. Then we parallel transported a distance dB to the left. This adds more changes. Then we parallel transported down a distance dA on the left. And finally, it's transported back to its original location through a distance dB to the right. The end result is the orange arrow. The orange arrow differs from the original red arrow by some delta v, here seen as a little green arrow. The Riemann curvature tensor is the object that tells us how much and in what direction little green delta V is pointed. Zero curvature means zero delta V. We walked it counterclockwise, but if we'd walked it clockwise, the change would be in the opposite direction. A logical question might be, doesn't going back and forth along the same distance just cancel each side out? And that is a great question. That idea is called the commutation of vector addition, and in Euclidean space, that is always true. It doesn't matter the order in which you add vectors together. But in a curved space, it does. Vector addition does not commute in curved spaces. The Riemann curvature tensor encapsulates that non-commutativity into one hairy-looking expression. Here we can trace the progress of the metric through the curvature. We see that if we start the metric in 3 spatial dimensions, we don't have anything along the way that adds more spatial dimensions. Each of the mathematical tools just uses the metric in more and more detailed ways. We saw that the Christoffel symbols are composed of the first derivatives of the metric, and those show the gradient along a geodesic. However, the curvature tensor is composed of either derivatives of the Christoffel symbols or the product of 2 Christoffel symbols. Either way, that means the curvature tensor is composed of second derivatives of the metric. That is a change in the gradient of a path. A constant gradient or angle is not curved, but a gradient that changes is curved. But again, what's it curving into? Again, the space itself has a property that we call curvature, and that has important analogies to hills and valleys and slopes and arches, but those analogies break down when talking about spaces that are not Euclidean. The structure of the space itself has certain properties that make vectors change their orientation and magnitude as they are transported around loops. An important side quest to the Riemann curvature tensor is the Ricci curvature tensor. We see that it looks a lot like the Riemann tensor, but we're summing up on the first and third indices. To indicate this, I've changed rho and mu to A. I've also changed index nu to I and sigma to J. For those in the know, I've skipped over the Bianchi identities and the resulting antisymmetries that lightly change the order of a couple of indices. The Ricci tensor is a slightly different measure of the curvature of a space. It shows the change in the volume of a space that is bounded by short hops along nearby geodesics. If you take 2 geodesics that are initially parallel, they will bound some volume in space. Now, walk a short distance along both geodesics and measure the volume between them. The Ricci tensor tells the change in that volume. Why bother to make this thing at all? Well, remember that we eventually want to relate this back to physics, and we need to know about volumes in physics, and very often what is exactly inside that volume. I've of course skated completely around the derivation of these tensors, and I'm just handing them to you, like a croquembouche baked by a master French pâtissier. I'll have to do a full derivation video on this at some point. But if you're dying to learn, then I'll have to leave you to study proper books on relativity, such as those by Weinberg, Wald, Schutz, Hartle, or even the epic Gravitation by Misner, Thorne, and Wheeler. It's really important to point out there's a huge mathematical formalism that underpins the study of non-Euclidean geometry. Even current topics in cosmology that have arisen due to the Hubble tension that explore modifications to Einstein's general relativity, they all use the same mathematical constructs, proofs, and theorems. This is the language of spacetime, no matter the physical process you're studying. Now let's see why the Ricci tensor is important. To help understand why the Ricci tensor is so important, let's calculate just one component of that tensor. We have our tools across the top. Up in the upper left-hand corner, inside the green box, are the 3 components of our metric. And in the upper right-hand corner in the purple box are all the Christoffel symbols associated with that metric. And what are we going to calculate? Below them, on the left, we see R sub RR. To get that expression, I substituted R for I and J in the Ricci tensor definition from before. And as you can see from the 4 terms, we still have to sum over A and B. I'm just going to skate quickly across these to get to the punchline. The first term is in red. Of all the possible parts, only 1 remains. The second term in orange keeps all its 3 terms. Note that in both red and orange terms have derivatives with respect to R. This indicates we're looking at the change in the gradient through space as we get further from the origin. In the next line, we see the term in blue. That's the third term in the defining equation. Because we're summing over a and b, for each one cycling through r, theta, and phi, we could have had 9 terms, but lucky for us, 6 of these terms drop to 0. Lastly, the purple double sum also drops down to exactly 3 terms. In the next line, I collect all the terms together, and it sure looks really hairy right there. But amazingly, after doing the algebra and the differentiation, plugging the values of the Christoffel symbols into the formula and chugging along, almost everything cancels out. We're left with an extremely simple result you see at the bottom below in yellow. It just so happens that for this particular metric, which is an isotropic, homogeneous metric with a constant uniform curvature, the Ricci tensor component for this one term is very simple. It's just twice the curvature constant times the metric component that matches the tensor's indices. Now let's see what the others look like. Strikingly, there are only 2 other components to the Ricci tensor, and I've given them in the green box. On the left, we see the guy who started it all, Bernard Riemann, who back in 1867 gave lectures on non-Euclidean geometry. His set of lectures had an enormous impact on mathematics. The first impact was defining the concept of a manifold, which became our modern idea about space. A space, or now manifold, is dense with points, and you can lay down a ruler, or a metric, to measure distances between them. And by dense, we mean that there are no gaps between points in the manifold. You can always slice a piece of space in 2 and find there's still more space there. Basically, a manifold space is continuous and smoothly varies from point to point. The idea had profound impact on group theory, representation theory, and the analysis of the real numbers. It was also the spur for the creation of algebraic and differential topology. This fruitful line of work also gave rise to Einstein's general theory of relativity. To see how, we now have all the components for a tensor that describes the deviation of a volume from Euclidean space. Our metric gave rise to this extremely simple form for such a relationship. The Ricci tensor for this metric is just twice the curvature constant times the metric itself. For the near final trick, I'll define the Ricci scalar R. This is the metric summed over the Ricci tensor. We call that process contraction because it reduces the total number of indices of a tensor by 2 for each contraction. The Ricci scalar is a double contracted Ricci tensor, which itself was a contraction of the Riemann curvature tensor. The Ricci scalar, or curvature scalar, is just a number that measures the curvature of the manifold, read here space, that is covered by a particular metric. For the metric we developed and worked with throughout this video, the Ricci scalar is exactly 6 times the curvature constant of the metric. Finally, we have what's called the Einstein tensor, which is a construction of the Ricci tensor, the metric, and the Ricci scalar. It's been proven that this is the only divergence-free tensor that can be constructed from the metric. This is really important because something that is divergence-free in physics is a conservation law. Einstein understood the importance of this tensor to general relativity. This tensor is the left-hand side of his field equations, which relate the energy density of a space to its space-time curvature. That's why the guy is smiling so hard. When he figured out that space-time curvature can be thought of as conserved in a similar way to matter and energy density being conserved, he knew he'd found the link between space-time curvature and its contents. Cosmology is, if nothing else, the study of how space-time changes due to the evolution of its constituents. Einstein had to become very well versed in the mathematics developed 40 years prior before linking gravity to space-time. I'll talk about the natural extension to this metric next time when I discuss the Friedmann-Robertson-Walker metric. Wow, that was a lot. I hope you enjoyed this video. If you did, please subscribe, hit that like button, and share it around on social media. I also want to invite you to become a YouTube member. You'll get videos like these earlier than everyone else, plus you'll get little bonuses. Or, if you prefer, please become a Patreon supporter. Both kinds of support go a long way to helping me get more of these videos out to you. Thanks again for watching, and we'll see you next time.